Hello everybody, welcome to the stream. Good morning. How are you guys? Anybody there? Hello Alco Checo, welcome to the stream. Yeah, okay, cool. Nice. Great. Yeah, so I actually cleaned up the code yesterday from what we did, and what was the issue actually? I think this is a part number or something. I think the issue was like there were some stupid mistake. I think I was just tired. But basically I had this, let's just double check. When I was generating this expression, primary. Yeah, so here. So you don't want to like load an entire array into memory. So we had like an if statement around this one, and that was like placed 2 times. So that was the entire reason that didn't work. We had that 2 times after each other. So that was the reason why we got these 2 loads into memory. So I removed this, and we also had it one other place in the code as well. Yeah, here. And both of these statements has to check this thing. So I just place a check inside the load instead. So the load is actually going to check if this is an array, and it's not going to attempt to load an entire array into memory. So now it actually works. That was literally everything I did. Just remove that duplicate statement, and I cleaned up the code a little bit. So I think it looks much more cleaner now. Yes, we're making a compiler. So now we're going to take a look at structures, and my starting soon is still displaying. Yeah. So like I didn't clean up that much. The main part I did was just I made function calls for everything in here. So all the sub expressions, I had like a huge switch here yesterday. So I just made function calls for each of those. I think that's cleaner. And the same the typer, like all over the place. I just made these function calls instead. So that was literally everything I did. But again, it was just this duplicate load, which was the issue. So now it works, or it worked yesterday, at least. Cmetrics is still displaying. Looks terrible. What looks terrible? Yeah, starting soon still displays. Welcome to the stream, by the way. So what did we do last time? If somebody wasn't there, we did pointers. We did like control statements, loops, if statements. So now we can actually write much more in this language. So our if statements are actually inferring what's here. I think the inference working. It's not the right language here. So we can say for I in 0 to argument count -1. This is supposed to be given by the operating system. So this is going to iterate through all the arguments. And now I can just say argument is something, and I can either do like argument of an index here. That should work. And we're getting argument is this. So this is actually what I'm calling the, the compiler with. No, the application with. You can see it in here. Is this a little bit too small maybe? That's better. So I'm calling the executable with some arguments. So this is what's displaying. And note that the application itself is the first argument, and it's always like that in the C world. Or I guess any parameters passed in Unix is giving the first argument as the actual program itself. Yeah. Global scope variables expressions. Global scope variables. I'm actually gonna take a look at that now. Global scope. So global variables. They're still being parsed. So if I like have a global variable, it is still being parsed, I think. Yeah, it is still parsing it. We have a declaration variable, which is the global. So we probably have to mark it as global because it is not really allocated on the stack. This is gonna be sort of like the strings. It is just gonna be placed in like a specific section, like the data segment. So that's a good idea. We're gonna take a look at that. Let's just check if the pointer thing work. So I'm gonna do argument pointer, and this is gonna be inferred the value that argument is pointing to. No, so this is a. I'm gonna just give it the value of arguments, and then we should be able to say the value at argument. This is the new syntax. I had to change the pointer thing. So that was also something I changed, and now pointers are still the same, like in C. But when you're, if you would have like a triple pointer, so I'm gonna say like variable is a triple pointer to char, then I have to give it the address of these arguments. So then I can just say this. So this is like the address operator and pointer operator. This is the deref. And I like the symbol, like this is, and it's pronounced like at. So this is the value at argument. So that makes very sense for me. The only drawback is that this is maybe a little bit hard to type fast if you don't have a programmable keyboard. So I changed that, and after this we can do like arg +1, and we should get the same thing. Yeah. So pointers are working, and this is now not incrementing with 1 byte, it's incrementing with 8, because this is a pointer to 8 bytes. So all that is working, which is very cool. Yeah, so we're gonna have a look global variables. We're gonna take a look at that now. That totally makes sense. That's what I also have in my compiler. Oh, is it? That's cool. So I'm not like totally off. That's good to know. Yeah. I guess it may be hard to type. That's the only drawback. But you can use array subscript instead, and that's easy. Yes, this is working. We also have for like conditional statements, so if, and we don't need to do the parentheses, so we can say like variable is equal to 5, do something else, do something else. Let's have a variable equal to 5. So variable is 5. I haven't really checked if the else if is working. So variable is equal to 3. I'm gonna just say like variable is something at the very bottom. Declaration is existing. Okay, so we have a duplicate declaration here, which is wrong. This is not supposed to duplicate that one. Yeah. So what's happening here is that we have a scope. We're opening a new scope for each of these compound statements. And each of those compound statements has lists of variables and various declarations. So when I want to make a new variable like this, it is going to first look up in the current scope if that's already declared. And apparently it seems like the algorithm are looking up in previous scopes as well, which it is not really supposed to do that. So this is parse declaration, and eventually it pushes something on the current scope. And this is pushing on the scope, and here we check if this actually exists before. So we have to go in here, and this recurses up again. So we don't want to do that. This is not allowed. So we don't really want to recurse there. And then the problem is like, what if you have, what if you have some kind of statement like this, or like a function or something, because this is a separate scope. So I can't really track that. So this argument should actually be going in here instead, because I need to check that. We can mark it somehow. If we remove this one, it should work then. Anyway. So now it says the variable is 5, because it's 5. If I change this to 4, no. If I change this to 3, it's gonna give me 3. So that's the else if. If I change it to something else, it's gonna give me just variable is. So if statements are also working, which is very cool. What more? Yeah, so inference are kind of working. We can maybe take a look at that today as well. Not something crazy, just supporting multiple passes. Because if this would have been data, and data would have been declared down here, this won't work. So I want to support that this is being written. And then it has to just do 2 passes for this. And there's probably a better algorithm, but we can start with something simple in the beginning, just to make stuff work. Yeah. And structures. We're going to take a look at structure. That's the main thing we're going to do today. But yeah, that's kind of cool. Okay, let's take a look at global variables first. That's fun. I'm just gonna do uninitialized global variables, I think. I think it will do uninitialized global variables. Like this is, as far as I know. Let's open the assembly file. And I want to change something else as well. I just remembered. This is gonna be something like data, and then you have like a label. And this is a U64, so I don't know the syntax, but this is probably like long and 45. And if I had like an array of 2 of those, it would be long and long. So that's how the assembly is going to look like. But I don't want to take that now, because maybe we're going to have more like default initialized variables. So it might be a little bit different. I don't know. we're gonna just place the local variables and assign some kind of space for it. And just set aside some space in the data segment. But first, I want to remove this because this is very ugly. This is very ugly. All those strings. Yeah. So I want to place that in a different section. Probably in a different, I want to place it in a different place. I want to have this in like a separate place at the very bottom. So that'll be here. At the very end I want to have this. And if I have multiple strings, I want to have them all underneath each other. 2 seconds. My phone is calling. Phone is ringing. BSS, yeah. It's going into BSS. These uninitialized variables. So I want to have something like this. And this has really to go just in a buffer. I have to make a buffer for this. And we can either just like allocate a lot of memory for that, or we can make some kind of dynamic buffer. So I think we're gonna go with the last one because it's a little bit cleaner. And we don't know how much we have to emit here because these strings might be very big. So I'm gonna go with a dynamic array kind of thing. So I'm gonna make a new file called array. I don't know if that's the right word. It's gonna be like called something else. But I'm gonna call it array for now. So array.h array.c. We need std_lib here. I'm gonna allocate some memory. And here, this is my worst word, if not defined. And if. Okay, so I want to be able to like push things into an array, and that's gonna grow dynamically bigger. So I want to have a structure first to describe this kind of thing. And it's very simple. We're not gonna have any pointers into this array. So we can very easily just allocate a new array, which is, for example, 2 times bigger, and then we copy the initial content into the bigger buffer. We can easily do that. So I'm going to include typedef as well. And then we're going to make a new typedef. Array. We might need this for something in the parser as well. I'm going to call it array now. Maybe I'm going to reuse it to for something else. Okay. So what do we need to have? This is going to grow dynamically bigger. Thank you for following. Welcome. Yeah, so this is going to grow dynamically bigger. So we need to some kind of store the current size. And we need some kind of buffer. This is going to be used for chars. I'm going to use it with chars. This is a nice place where you can use like template programming in C++. So we need a char pointer buffer. I'm gonna have an index to where I'm gonna write. So this is like how much the buffer is filled. What is the word for that? Buffer size index or something. Capacity, yeah. All right, that's much better. Thank you. Capacity. All right. Thank you very much. So either we can just allocate it. I'm gonna just ask for a new one. So this is gonna return me an array. It's not gonna take in anything. We might be able to specify an initial capacity, but I'm just gonna choose something. It doesn't really matter. It's gonna grow anyway. And then we're gonna make a function void array add. And we need to be able to do formatting in here. So I'm gonna make one add and one add format. So the add format is gonna take in some data and some dots here. And the array add is just gonna add the data. Yeah, perfect. So array add and array add formats. So let's implement those. And by the way, I'm using these 3 dots here, so I'm gonna include std_arg. What do you think about my new color theme? I actually like it a little bit. It's very subtle, so it doesn't strain your eyes too much. I like the colors, but it's a little bit too many colors though. That's the only drawback. Standard arg. Yeah. Never heard that before. So I'm gonna use malloc here. I'm gonna use malloc. And the size is gonna be, I'm gonna give it initial size of 1024. Let's make that a define. Const u32 1024. And then we're setting the array capacity equal initial size. This is not really right. I'm gonna allocate the array first. Array first, and then we allocate the actual data. Initial size. Size of. Yeah, size of. That's right. This is just gonna return the array. For the data, I need to know how much I'm gonna add. Or do I really need that? No, I can just start placing things inside the buffer, byte after byte. So I'm gonna iterate through this entire data array, and I'm gonna try to push one single char. And we might end up doing something similar like here. Because this is kind of specifying the size. This doesn't. I'm not really gonna care about the size now. So I'm gonna make a function for add char, which is a static one. Static void add char. And this also needs the array. And by the way, we need to have the array here as well. Purpose of static, it's not supposed to be used elsewhere, like in a different file. Less work for the linker. That's probably the best reason. So add char. So while this data is something, we're gonna call array add char, and this can probably be inline. Static inline void add char, and we're gonna call it with array and data plus plus. And then if this exits, or if some kind of malloc fails, I'm gonna just exit from this function there. For the format thing, I'm gonna do va list va start argument and data. This has to be the element before ... So here I'm gonna describe the variable argument list, and I'm have to give the argument before that. So size is equal to vsn printf. Yeah, it's that one. So I'm gonna be needing a buffer. So I'm gonna say static char buffer. Gonna give it 2096 or something. No, 2048. Yeah. So I'm gonna print to this buffer, which has this size. The format is just the data, and the arguments are arg. And then this is going to return to me how many bytes are written. And then I can simply do for I is equal to 0, or let's use a while loop here instead. So while size minus minus, we call array add char with buffer. I kind of have to use a pointer as well. Pointer is equal to buffer. Something like this. Set the size to 0. That's a good point. Thank you. What type of grammar are we basing this off? This is not... We're just trying to make this so that it's nice. Like taking some inspiration from C, taking some inspiration from other languages, and yeah. We're not defining any syntax first and then we're writing it. So add char. Okay, so if the capacity is 1 and I'm pushing 1, yeah, so first I'm gonna check if the capacity, I'm gonna check if the array size is bigger or equal to array capacity, I'm gonna allocate a new buffer. A bigger buffer. And then we just push the byte here. So this will be array buffer of array size plus plus is equal to char. And then we have to reallocate a buffer here. So I'm going to do a char pointer, new buffer. Thank you for following. Welcome to the stream. So I'm mallocing this array capacity times 2. So I'm doubling the capacity each single time. And then I'm memcopying over. I could probably use memcopy from the standard library. Is that in string or something? I'm just gonna do it manually. So for I is equal to 0, and we have to iterate up to the array size. -1. Array size +1. Array size +1. Is it like that? No, is it? Like if the array capacity is 1, then this is going to be 1. No, that's not true. I'm going to allocate if it runs out of memory. So if this is 1, and this is 1, I have capacity 1 and size is 1. And if they're equal, then I need to reallocate a new buffer. I'm placing bigger or equal. Just if I'm messing up this pointer somewhere else. Okay. Anyway, we're iterating up to array size, and then we're copying over the array. So array buffer of I is equal to new buffer of I. So now everything is copied over, so we can replace the buffer. And we're gonna free this previous array buffer. Well, let's do array buffer first. So you're freeing the buffer, and then we're linking in a new buffer. And the capacity has to be increased as well. Something like this. New buffer. We can probably save the size first. It doesn't really matter. If I'm saying like char old buffer is equal to array buffer, and I'm actually using the new one here. No, I'm not gonna do that. Doesn't matter, it's gonna work inside the for. Yeah, totally right. Thank you very much. I went a little bit quick there. So array buffer. So double check if this is bigger or equal to the capacity. Basically, if you have size, this is gonna work. If we have size 1 and like the capacity is equal to 1, like the size is 0. So this is the initial thing, and you have the size 1. So the first thing you're gonna do here is you're gonna check if this size is bigger or equal. So this will fail. So you're gonna push this array and increase in the size. This is gonna be changed to 1. Then you have filled the entire buffer. The next time you will actually do this. So I think this will allocate in place in time. Yeah, if this malloc is failing, this is an generator probably. I'm gonna just say array. Malloc failed. All right. So now we should have a dynamic array. Out of memory exception, yeah. That shouldn't really happen. Is it possible for the capacity to be 0? No, because we're setting it to initial size there. So if you're changing this to 0, yeah, but you're not supposed to do that. Yes. Okay, so now in the generator, we can make a new array, which we're gonna call like the data segment, and then we can actually emit the data segment after the function. Each single function is gonna have its own data segment after the function. So I'm gonna make a new array. I'm gonna include it first. What are you gonna call it? I'm gonna call it data segments. Data segments. This is gonna be a pointer. And the first thing we have to do, we have to initialize this. What is it called? Like array? New array. So I'm gonna add a new array and we're gonna place it in the data segment pointer. This is just a pointer. So now we should be able to emit to this thing. So I'm gonna make 2 new functions, or probably just one. Which is gonna be called like emit data. Emit data. There we go. Wait a second. I probably want to have one like an array function with the actual argument this as an input instead. So something very similar like this, but where I don't do that. I'm not going to be using this like usually. So you're going to say add VA list. And yeah, so it's basically the same as this one. Instead of taking in the dot, we're gonna take in the actual list. So then we can make functions which looks like this, which is calling this one. And this is the list. I'm gonna do that again. We're gonna copy this part, which is using the arguments. We're going to copy this buffer. And we're going to copy that one. And then we can just call into that function here. So add VA list, array data, arguments. Isn't that gonna work? We're making a compiler. How advanced? It is not very advanced. It is like once you know how it's supposed to be done, it's very simple. Like once you really understand it. But I don't think I've understood everything. Like, I would like to understand this a little bit more. Just the thing, like, just this I would like to understand a little bit more. So I will probably remake this in a new language at least once before I would say I know how to make a compiler. Because it takes time, like you have to do it. Like you can't really know exactly how to do something the first time. You try to do something and you note the errors and you note what was difficult and you try to do it again better. That's at least what I think. But the hard thing is knowing what to do. If you know a little bit on what it's supposed to look like, it's not that hard. Yeah. Like this is made from 30 hours, like 3 days. And probably 50% is just me messing around with stupid stuff. Okay, so emit data. That is gonna call array add VA. We're gonna make a VA list first. Let's change this to data instead. So VA list and VA end. Thank you for following. Welcome to the stream. Thank you very much. So we need to provide an array. So I believe that is a data segment, which is initialized. And the data is just the data. And I'm going to use the argument list here. So this is supposed to emit everything. And we can actually, I don't know if we're going to make functions for it. We're going to kind of print whatever's in this array. And then I have to modify the size. So I'm not sure if I'm going to make functions for reading stuff out of it, or if I'm just going to modify it myself. I think I'm going to just modify it myself. So this is emit data, and we're going to make one for emit the data segment. And this is just the void. This is going to emit everything in this data array. So here, I want to say emit data first. This is going to make sure it's a data segment. And then you emit whatever's in this array. So this takes in data and ... I'm gonna make one emit for count. We can probably just use this file write. I'm gonna use that one instead. So we want to do file write. From the buffer. So this will be the data segment buffer. And data segment size and a file. This is going to print everything. And then we just have to make sure we set the data segment size equal to 0 again. So that's it. And let's have a new line before it, because that's kind of nice. Do you think vector in C is bad? You mean C++? To be honest, I don't know how vector work in C++, like underneath. I guess it's doing something similar as we're doing here. But I don't know. I haven't really been using C++ that much. And C doesn't have arrays. Or no vectors. How did you get started with C? I started with Arduino. Like very tiny microcontrollers on PCB boards. So that's where I got started. It was really simple C coding, like making drivers and yeah, printing stuff to serial terminal and stuff like that. I think that's really cool. I love doing that. What assembly compiler do you use to convert it into machine code and link it? I'm using just these GCC. I'm using this. I'm doing a static. I'm assembling it static and outputting this file, inputting the output file. That's what I'm doing. Thank you for following. Welcome to the stream, newbie guy. So now I want to replace all the emit thing, which is actually emitting data. I want to replace that with the emit data. So here, I don't want to have data because this is going to be tracked when I actually emit this entire section. So we're going to emit data here. Yeah, and let's keep some space underneath it. So just for visual pleasure, that's better. And this I'm gonna emit once. I'm gonna emit this entire section after each single function. So when I'm emitting a function, after the return, I'm gonna emit this. Two few arguments to call array add char. Is that better? Oops. Junk event of line. Okay, there's something with the output here. So we're getting a very clean code here. And yeah, so the problem here is that when I'm emitting some data, I assume it's supposed to end with a new line. So I don't know how good that is. We can fix it by just changing the emit data function. So this is supposed to end with a new line. Add. Yeah. And we probably have to do data segment before. We're not emitting anything. What the hell? Makefile segmentation fault. If I don't do this, it is working. So there is something with this function. No, it is working. Okay, so I'm loading the string here. That's wrong. So I'm gonna remove this text, and I want to have this as a data string instead. So this is gonna be removed, and this is gonna emit code instead of data. So let's have it like this. There we go, and it's working. So now we have this clean section at the very end, which is sort of having all the data. And if I have multiple functions, we're gonna have one function here, and then the data, and then we're gonna have a new function. So let's try to make a new function. Let's try to make a function which prints some kind of board. So this is gonna take in I'm gonna print like the tic-tac-toe board. So I'm gonna have, so board is a pointer to an array of 3 U64s. And for I in 0 to 2, for j in 0 to 2, I'm gonna print the board. I'm gonna do what I was doing last time. So if board of I, j is equal to 0, I'm gonna print nothing, or just the delimiter. And else, I'm gonna print x. So this is if it's not 0. And here I need to print a new line. And I also need this up here. Okay, so let's try to make a data array. So I'm gonna say like some data has a 3 by 3 is a 3 by 3 matrix, and I'm just gonna print it. And remember, I'm using this star. This is the address. I'm giving the star of data because this is supposed to get a pointer to this kind of thing. Now we have a duplicate declaration. It is existing up there. So I'm going to use board instead. And define reference to prints. I also want to do, because I'm actually doing some type checking, I'm doing some checking if the function actually exists. So instead of having to disable that completely, I would, for example, if I can mark this function that it's extern, so just during development of this compiler, I can define different functions as extern. So the compiler is not going to check their name. Something like extern. Something like this. Extern or something. I don't know. So we have an array here. We have the board. Let's try to initialize it first. So we're going to make a function for initializing it. Almost the same thing. And this is called init. And we're going to also call it with the address of the board. So this is actually going to change whatever this is pointing to, which is on this stack frame. So now it's 0. And if I, after this, do like for I in 2, for j in 0, 2, if I equals j, board ij is equal to 4, something. I'm gonna get this line. Yeah. It's like 3 in a row. That's cool. So that's multiple functions, and we should see that it's emitting this right. Yeah, so we have the data section here. We do not have any data segment here, but it's still emitting data, which is a little bit stupid because it doesn't have any data. So I should probably restrict and say if this is, if data segment size is equal to 0, just return, because then this is going to go away. And then we have some strings here. I can maybe remove this. That might be a little bit cleaner. I don't know. I have Arduino in a box at home, never touched. Any recommendation for a fun beginner project? That's cool. That's a good start. Really good start. It depends on what you have like in hand. You can't really do very much cool with Arduino without any like sensors and stuff like that. But if you have like some switches or some potmeters, potentiometers, like some variable resistance. I don't know what it's called. I should know that. You can just hook them up and try to read some sensor values and print it to the terminal. And the Arduino actually has like a USB to TT, USB to serial converter. So you can just print serial to the Arduino terminal. But what I would recommend if you're going to use Arduino, I would recommend installing, I don't know if there is some better way with using AVR, but I would be installing Atmel Studio, or it's called Microchip Studio now. They did a rebrand or rename. And then you can actually program the Arduino in C instead of Arduino. Because I wouldn't really recommend Arduino, the Arduino language. I wouldn't recommend that. So just Google how to set up the Arduino in Atmel Studio, whatever, and it should be doable. And then you can write in plain C. And then you have to use a datasheet for getting for like knowing what to set and stuff like that. So I believe, let's see. This is a little bit of a sidetrack, but that's fine. It's gonna just take 2 seconds. For example, this one. This is the one which is sitting at some Arduino, I don't know which. But then you can just go in here and you can see like it has some IO ports. So I'm gonna go in here and to the register description. And so this is the register you want to set. And this has some address. But I believe Atmel Studio has some API for this. So you can just write port B in capital letters. And I'm just gonna pop out what you can write there. And if we're writing the direction to 1, which is sort of setting the pin as an output, and the data to 1, you're gonna see like the LED is lighting up if I connected any LED. And then you can start toggling it. It's very cool. So I would recommend using this instead of Arduino if you're gonna learn. Arduino is very nice for just rapid development, I think. Anyway, that's a sidetrack. Okay, thank you very much. I'm gonna store this. I'm gonna take a look at this because I'm very interested in that. I don't know how that's being done. So thank you very much, Ensybot. Thank you. I would say 4th, but McCrisp is not available for Arduino. This is, however, available for the Blue Pill. Blue Pill is cool. That has like a lot of powers. I think there is some cool TFT LCD display projects with the Blue Pill. I think that is the one which is able to like stream video to a TFT display. I don't know though. And Stellar Strip as well as the TI 16-bit launchpad. I haven't used that. Board should be defined in 2D. Board should be defined in 2D. Where? It is defined in 2D here. And then I'm just taking a pointer to that. Which I believe is a little bit like, I should also be able to do this. It is a pointer to where I can find the array. And then I have to dereference it first. So I believe I have to do like this. See if this is working. Yeah, still gonna work. So like it is very difficult to understand. Like when I'm teaching somebody else, like when I'm trying to explain something in C, I just take it as a, I don't know what the word is. I don't think it's very difficult when I'm trying to explain arrays and stuff like that. But when actually thinking about it, it's very unlogical, in my opinion. The array pointer duality in C. I don't know. we're planning to adding tree-sitter support for your language. Syntax highlighting support. I'm going to just do something very simple in VS Code. It has some extension. You can make syntax highlighting here. But I personally doesn't prefer that much highlighting. I like this. But I would like commenting to be highlighted and probably functions or these big things. But usually I don't like the highlighting stuff. So that's actually contrary to what I'm doing here. With like way too much colors. Like this is, yeah. So we went with, the star, the asterisk for the pointer. Because I did so many mistakes. Yep. The right track. Okay, perfect. Nice to know. All right. Very quickly, let's for this string, let's disable that. So now we should get this very close to each other. So I like this. Global variables. Let's take a look at global variables. They should be very simple. I'm just gonna mark it as some kind of variable and do 0 and a number. I have to check that out. AT 0 data. Here we go. Global variables. Begin, let's jump, compare, colon convention. Was that everything? Oh, here we go, data. Byte 64, declare a byte containing the value 64. So this is for initialized data. And here we can use like 0 data. So I'm just gonna start with 0 data because it's very simple. So we can have global variables. So if I want to have like a big array, I can just define it like this. Yeah. So first we have to recognize when a variable is global. And I don't really know how to do that. Like, what is the best way? It is sort of the first scope, which is a global scope. So I have to go down here. It's generating the global scope. And this is generating a function. So we're not declaring any variables in a scope. And a function will go over all the subscopes in the compute local variable offsets. That's interesting, okay. So we can actually get the local variables from here. Generate scope. And we know if this is a global scope. So if scope am I calling generate scope just once? This is only once. So we can check if the scope has a parent. If the scope has a parent, it's not global. If this is 0, global scope. And we're going to iterate the scope variables. Oops. And for each thing here, we're going to make a declaration. We're going to say list to okay, so we have a declaration. Let's just print something here. So new global variable. Let's see if we have someone. Okay, so this was supposed to happen after this. Oh, I'm not having a global variable. I'm gonna make one. Test global. This is a an array of 50, 60, 64s. So now we have a new global variable. So what we're getting is this declaration here. And we probably have to just assert that that's not initialized by some value. Or just ignore it, I don't know. We have to see. Add luxury to VS Code, that would be nice. Coworker asked if I was colorblind when he saw my syntax highlighting. Oh, because it was too much or too little? Some like colorblind people used to use these weird colors because they're like, I don't know how it works. I don't think I'm colorblind. Neat even code generator. I'm outputting assembly, yeah. I destroyed machine code, that was fun. That's we're also gonna plan to do that, but then you have to do the linker stuff yourself. And especially if you're gonna compile this to controllers which has embedded Flash, which I'm gonna be doing, then you have to be able to relocate the data segment, because the data segment has to go in Flash, which is read-only, and then you have to sort of mark, like the code you're writing here has to know where things are being placed, if that makes sense. So we're going to copy the data from the read-only segment to RAM, and then you can start executing it. So you're going to have like, yeah, the address is going to be not where it's placed. You dabble with the Raspberry Pi? I haven't dabbled with the Raspberry Pi. Oh, it's fast for... nothing fun about it. Feel... I don't know what JIT means. Float assembly is neat. Implement fpic. Probably. Annoying to code. I guess I have something to look forward to. Just-in-time compilation. Yeah. Okay. I don't know what it means though. Compilation during execution of a program. Oh yeah, it's a bytecode. Okay, yeah, I understand. Yeah, we're gonna make a little interpreter. You're going super fast with this language. I've done it kind of before. Not exactly this, but something that was really horrible. So I had to remake everything. And I just thought I would do it on stream instead. It took a while to get to this point, to be honest. Because I think it's difficult when you haven't done it before. And I've been only programming for a few years. So I would not say I'm very good at programming. So I think it's hard. But I also think I'm learning, so I'm very happy about that. You have to start somewhere. Native code on the fly. Okay, I understand. Broken. Bitwise. Is that a YouTube guy? The Russian YouTube guy. There is one guy on YouTube which tells how to make a compiler, but it was way too much like Lex and YY and what is it called? Like YY yak or something. Yeah, it was too much for my taste on that. Anyway, we have a new global variable. Actually, let's print the size here as well. So declaration, this has a type and the type has a size. Oops. So we have a new declaration which is size 448. So I'm just going to give it a label, and this is a new global variable. So let's think about the name here. Yeah. All the globals should have a unique name. I can just use the name which is given here. So I'm going to emit the data. And I need to have a label first. This is just string. I'm going to call this I'm just going to say global and get a label, and we're going to use the declaration name. Alright, so now we're emitting the label, and then we're going to emit 0, and we're gonna say how much we're gonna 0. So this is explaining how many bytes I'm gonna allocate for this global variable, which is defined in the declaration type size. So I can use that one. Let's just use the declaration name. I think it's a little bit cleaner. Okay, that's good. That's good. So this is emitting the global variables. So if I now run this, where is it? Where is it? Oh, we're not emitting it. Okay, so we're generating first. We're generating the function first. I don't know where I'm going to emit this. But yeah, probably after the function. So I'm going to have like emit global data. And then we emit the data segment. So then it's going to go in here. And we have the global data there. Okay, I'm going to delete the global data. Okay. So global test global. I'm going to remove the global thing. I don't think that's needed. It just makes it more annoying to look at. So we have test global, which is just 0448, which is the size. So now we can load this address here into memory. So now we need to figure out if something is a global variable or a local variable. So we kind of have to mark this as local or global, because we have to know how to load this into memory. Okay. Any idea how we're going to do that? We're going to do it in the parser. So we're parsing a new code unit here, and this is the global scope. So we can make it very simple and just iterate. Parse block. We can just use this compound statement here and iterating over all the variables and marking everything as global, instead of having that as a function call. So we can just go over everything afterwards. Go over global Globale. Global. Is that the best thing we can do? Probably. How old are you? I am 24. 24 years old. Flex Bison usually. Oh. Bummer per doesn't cover actual code generation. Oh, yeah. It's covers C code generation, which was close enough. I haven't watched him. I'm very interested in this kind of stuff. Thank you very much, though. Aren't really hard. The hard part is the optimization backend. That is right. I've heard that that is the thing. And when actually knowing how to do it, it makes sense. Which is why we only have LLVM. I think you can make some decent optimization passes without using LLVM. So like when I'm using, I don't know how much optimization GCC does if it uses O0, but I think it has a register allocator, but doesn't do anything more, like O0. And I had this operating system, and I benchmarked O1 compared with O3, and it wasn't that much faster. It's like, I can't remember, like it was, I think 25 or 30% faster. It wasn't that much. So I don't know how much optimization really has to do, like really has to say. Is it really gonna speed up the code with like 10 times? Assuming you have a register allocator. So you're not doing what I'm doing here. But how fast is really that's gonna, like how much improvement is an optimization, like for example LLVM gonna have? I don't know how to say it. Is it a tic-tac board? Yeah, it is. We're testing that the arrays are working. O0 is debug. We fight for every flop. Yeah. I think it's more important to have a language that is easy to code in and you don't make errors. Yeah, I don't know. It's, if I want to have this optimization like really, if I want to optimize really hard, I can just make an LLVM backend. That's fine. But I'm not compiling to get the craziest speed. I'm compiling to learn. No, I'm programming to learn. So if I'm gonna use this compiler, I want it to be easy to program in. And if it's fast, it's a nice thing as well. And if it generates fast assembly, it's a nice thing. Anyway, I'm messing around. Okay, so we have to mark this as a global variable. In other words, we have a declaration somewhere. We have to mark this as a global variable. Yeah, so I don't know if that's applies on a function as well. I think it applies on a function, so I'm gonna have it here. It's global. And this is just temporarily. So I'm gonna iterate the statement compound. This is gonna return a compound statement. Scope. This is the top level scope. And we're asserting that this statement kind is a compound statement, and we should be asserting that it doesn't have a parent scope. But this is implied. This is always going to be true. But we can still have it there. My keyboard is messed up. Almost. Okay, declaration. We're just gonna mark this as is global is true. So now, when we generate the address of something, of a variable. So if this is a variable, I also made these functions for checking if something is a variable, because I first need to check if the kind is a primary, and then if the primary kind is identifier. So that was kind of a little bit ugly, so I used this function here instead. So I'm asserting that this has a declaration, and then we're gonna check if expression primary if primary declaration is global, we got a global variable. So I want to see this, and that's gonna happen if I'm using the code, using the variable in the code. Error scope is a pointer. I'm gonna go to the scope and list all the variables. So it's still not breaking. I'm not getting any global variable. And that's probably because I'm not using it. So if I'm using it here, 5 is equal to some value, I should be getting a global variable here. So I don't know what assembly this is generating now. Probably the wrong one. Where am I testing? There we go. So it's moving. It's moving 3, 4, 5 into racks. And then it moves 8 into racks. Okay, so it loads 0 and RBP. It tries to get the offset, and since this is a global variable, it doesn't have an offset. So therefore the offset here is 0. So that's what's being happening now. And we're gonna change that, because that's not really right. So I'm asserting that this has a declaration, and then I'm checking if this is a global one. And if this is a global one, we're gonna emit something different. We're gonna emit we're gonna load the address of this string into REX. And I'm gonna use the declaration name. Primary declaration name. All right. So now I'm doing that. Is this right? It's loading this into REX. I don't know if this is the right syntax though. I believe it is. So this is now loading test global into REX. What we can do, we can just print the address and see if that's right. I'm gonna print the pointer. Of test global. So we're getting the address. This doesn't seem right. Is that right? What is this color scheme? This color scheme is Everforest Dark. Everforest Dark. Yeah. Like, I'm just loading every single theme I can come across. I have this cool, there's a cool site like VS Code themes preview site where you can download this kind of thing. It's very cool. I like themes. Yeah, it is almost random. Thank you for following, Samuel. Welcome to the stream. If the gray background was a little bit beige, yeah, it can have like some changes to it. The printer thinks in your console that 3, what kind of 3 is it called? This is the syntax tree which we're generating. So this is just for like debugging, for making it very simple for us. This was something we made, and yeah, it is really very simple. Like, it is a graph structure in memory. The syntax tree is it's structured as a graph structure memory. So you have like nodes which is pointing to 2 different nodes, and so on. And this is just printing that in a nice way. So here we have an if statement which have a condition, a true body, and a false body, which has a new if statement. So this is a nested if, or like if, else if, and else. But the code of this is not very much, I think. This is in the tree printer, so it's in here. So I'm basically having this indentation mask, which is telling which line I'm gonna paint. And then I'll have this indentation, which is telling like where I'm gonna print. So it's very simple. It is just very ugly, like how this is structured. I had to hard code these numbers because there's no real way to do it like automatically. So it's a little bit error prone, but that's fine. Yeah, it's a syntax tree. Yep. Yesterday more. Yeah, probably. Are you into WebAssembly by any chance? No, I don't know what it is. I haven't been programming for that long that I know what WebAssembly is. I've heard of it, and I heard it's faster than something else, but I don't know what it's faster than. I like the pink imports. Okay, so now, yeah, the test global. Why the hell is that? Why the hell does that have a wrong address? Does anybody know if this is a right address? Does this seem right? Test global. I could probably just check the map file and see where that is placed. Can I do that? Object dump. Symbols and relocation, you can use this of an object file. Do we have an object file? That's not an object file. And I'll probably be deleting the object file. I'm not having that. Never mind. I think it should work. I'm just really like, why the hell do we have that kind of address? Because the stack is oh fuck, I'm using this. Yeah, okay, that actually seems right. Yeah, that's right. Yeah. I think so. That's also the way I'm doing it. I'm gonna do so I think what's happening, this is at least how I'm doing it. So I don't know how it is in like 64-bit, but in 32-bit you have a 32-bit address space, and typically, or I'm doing this. So I'm splitting this memory space into 2 parts, which is the 2 GB top address space and 2 GB low address space. So this is separated. This is reserved for the kernel. So the kernel is gonna execute here, And this is reserved for the applications. And what I'm doing, I'm mapping in the code here. So this is the code. And if I have some data, that's going to go on top of the code, like here. So this is the data. And then I'm having the stack at the very top here, and this is growing downwards. And then I have the heap on top of this one, which is growing upwards. So this is the heap. So it makes sense to have like a low address of the data. And then when I'm printing stuff which are in the stack, it's going to give me this high address. So typically on ARM, that address will be like, it's like, so 7 FFF. Something like this is going to be the stack address, and this is going to be closer to 0. So I guess that makes sense. I just didn't think. So I think we can say that global variables are working. All right. Yeah, let's take a look at structures. I want to be able to compile structures the same way we're doing in C. So I want to clean this up a little bit. So I want to use arguments of I, and we're just deleting everything. And we want to test the test some kind of structures. If I run this, it should just print the arguments, which I don't know what I'm doing. Argument is equal to argument plus 1. And by the way, I was looking at this yesterday. By any chance, does anybody know how to exit from a makefile if I'm having some kind of error? I tried Googling that. Like, for example, if I'm running this one. How can I just exit from the program? No. If this one fails, oh fuck, if that one fails. I didn't think about that. I actually tried to check if this one was failing. I want to check if this one is failing, and if the compiler fails because we have some kind of error, it is not going to try to run the program like it is here. If a rule fails, make will exit automatically. Yeah, but this is returning. Okay, I'm gonna go back. I'm gonna actually return 0, like an error code, if I'm having an error. Because I think I'm returning 0. Okay, nice. I didn't know that. That's perfect, thank you very much. So I have to return some kind of error code, and then I can stop it here. So now we know what's wrong, and we can fix it. And then it's working again. Okay, so one argument, that's fine. So now I want to make structures work. And we want to have 3 kinds of structures. We want to have anonymous structures, tag structures, and struct types. So I'm gonna do it similar than in C, just a different syntax. So we have type defs. So I can write some kind of type here. I'm gonna use the T symbol. And I'm saying that this is a use32. This is making T a variable since I'm having only 1 colon. So now this is making T a variable which has a type U32. If I want to make T a type, I have to do double colon here. So this is gonna type def T. So now T is gonna have the type U32. So now I should be able to do data has the type T and it's equal to something. So this is how we type def in my program, in my language. The same thing with structures. So if I want to have like a structure, then this token is going to be a type. I want to be able to write token is a token. So then this needs to be a type, so I have to do 2 colons here. So that's the type def. That's doing the same thing as up here. Anonymous structures we're gonna have. So I can write something like just structure, not the tagging with any name. So just this, and I can give it some kind of data here. And this has to be a unique name. This can't be defined here. This is gonna be an error. Why do we want this? This is very nice if we're gonna have unions. So I can make a union, and then I can allocate some structures. So this is used in some compilers. Like this is basically what I'm doing in the syntax tree. I'm just doing it more verbose. I'm splitting this up into multiple tag structures instead. But I think this is nice. If you want to mark the structure with something, let's make some members first. So this is an A member, and this is B, and this is C and D. All right, and let's have a union member as well. I'm gonna call it U. Okay. So now I'm saying that token has a type of token. So now I should be able to do token dot, and then I'm gonna access any member in here. So that can be, this is not supposed to be there. That can be data, because I'm not having a type name before that. So I can say token data, that's gonna access this field. Or I can say token C, and that's gonna access this field. And if I want to restrict this a little bit more, if I, for example, want to use C here, and I want to use C here as well, so I want to use the same name, I have to tag this structure. And then I'm basically using 1 colon here. What am I going to call it? I'm going to call it variable. And here I'm using 1 colon. So this is defining variable to have the type structure. So I think this is a really nice syntax. So now we can say, if I say token C, I'm going to give this one, I'm going to give this one. If I'm doing token variable C, I'm going to go into this structure and access this member. So that's what I'm thinking we're going to implement. Unions and structures are compiled the same way. So if it's a union or a structure, it is basically the same thing. The only difference is how we assign the offsets. So each each variable is going to have an offset from the base structure. So how do we explain this? I'm going to make a different example. Let's use tag structures. So this is structure A, and this has structure B inside it. Does this make sense? So let's say I want to generate code for token A B test. This is what I want to generate the code for. This is basically going to say I have a dot member which is called tests. So I'm starting at the right hand side. So this has dot member test, and this is a member in this structure here. So this is a member, is member of B, for example, struct B. How does that make sense to explain? I don't know. Basically, you're starting here, and you're going to the next one and next one and next one. And when you get to the final one, this is going to have an address. So token is just a variable, it's going to have an address. So we're recursing down first until you get the address, and then you check the a variable. And that's going to have an offset from this base structure. So this offset is 0, so then you're going to add 0 to this address. And this is giving a new structure. And then you're searching for b in that new structure, and you check the offset here. So this will have offset 4, and then you're adding 4 to this address here again. So you're just adding the offsets after each other. That's how it works. So we have to first parse this, and then we have to generate the correct address. That's really what everything is about. You have to generate an address for this part. I didn't know if that made any sense. Probably not. Unfortunately, I have to take some kind of English class. Probably. I don't know. Does an operator work? It doesn't. Not yet. I haven't added it yet. Is your program returning non-zero and error? Oh, there's a K flag. I didn't know that. Union sounds like you're combining structures. Yeah, so a union is basically, it is what it sounds like. It's either one of the member. So if I have like a U32 here and a U64, this union is going to allocate, this union is going to have size 64. And it's also going to have the alignment 8. It has to be aligned with 8 bytes because it has to choose the biggest alignment. Because if I'm going to access the member B, then this entire thing has to be aligned. So this is basically choosing the highest alignment and highest size, and this is becoming that size. And both of these members is having the offset 0. Like this. Yeah. Tagged union data structure. Okay, so I think I'm happy with this syntax here. We're gonna try to implement this. So we need to do, I think we need to do some changes in Elixir. We need to support this dot operator. And also, like, C should have been doing this like years ago. If you have a token pointer, which is a pointer to token, and you want to access some members here, you should be able to write dot. So dot A, dot B, dot whatever. You shouldn't be able to, like, you shouldn't need to write an arrow there. Like, the compiler knows exactly what type this token has. And it doesn't help with readability either. Like, probably just the opposite. It reduces the readability. Like, if you're having many pointer in directions, it might make the code slow. And by doing dot, it's probably hard to see it, but I don't think that's a problem. Anyway, we're gonna convert this pointer to a dot instead. Okay. Unions waste memory space because they always allocate the memories needed for the biggest member. That's correct. That's also correct. But it's very nice if you're gonna make like tree structures. So the way I do it is that I have so I have a union up here. So this is just gonna make all the members CAS compatible. So if I'm doing like expression, or if I'm doing binary, unary, primary, it doesn't matter. All it's gonna have the same address. And then after this I have a token, like a kind variable, which is telling which of these I'm gonna use. So that's a very convenient way of representing like graph nodes, because you can just traverse them and each node is gonna tell you what it's containing by just looking at the kind. So that's a very nice use for that. Yeah, okay, let's implement this. Lexer H. I also did some commenting here because this can be a little bit confusing, and I think this is very important. Just knowing how these work. So that should be displayed here. So we have the dot operator. We can just use this one. Yeah, we don't need anything else. So that's great. We can just start in the parser. Yeah, so we're parsing a program that is parsing one code unit, which is a file. That is parsing the top level scope, which is just parsing a compound statement. So what it does, it parses either a declaration or a statement. And if that returns anything, it's going to add it to the list. If it doesn't return anything, it is probably a declaration, and that is being added on the list anyway. So we're going to go in here where we parse either a declaration or a statement. And I'm first trying to parse a declaration. So this is where we're going to add the stuff because I'm going to make a struct declaration. This is declaring token to have the type struct. So we're going to go in here. Yeah, so this is where it happens. So this token here, the token variable, will point to token, and the next token will point to the double colon. And then we check if the token kind is not an identifier, or this is not a colon or a double colon, and then we just return. So if these two are true, we have something like either this or this. So we can parse that. So then we make a new declaration and we check if this is a type def, in which are recognized by a double colon, and we skip both of these. So after this stage, the token is pointing to the structure, the name structure, and we just check if that is a function. And then we check if a token kind is equal to a sign. So we need to check the structure after this. If token, I'm gonna search for a keyword. So I'm gonna check if this token has the keyword struct. Obviously we don't have that keyword yet, so we are gonna add that first. So we still have to add something in the Lexer. Struct and keyword union. If else in. So you're gonna add it here as well. This is just for the printing. So when I'm doing something unexpected, I can print what I'm actually expecting. So I'm printing structure and union. Struct. Oh, thank you. So struct and union. And this is everything we need to do. It's gonna check that against this. Actually, I'm not using this for the print. This is the table I'm using for recognizing the keywords. So now we check if this is a structure or is keyword token. Like, we should probably do 2 places, otherwise I have to check this again. This is probably a nice use of the bool. I'm gonna say no. Is structure is keyword. Keyword union. So this is either structure or union. I'm gonna check if this is a structure. It doesn't really matter how I'm gonna do it. So now we have a boolean if this is a structure. And now we need to parse it. So remember, this is pointing to the structure. So I'm gonna make a parse structure kind of thing. And this is a declaration. This is a declaration. I'm gonna make a type of this, because this is really just a type. This is a type, and we need a struct member as well, because this is not really a declaration. This is something different. It has an offset from the structure, and it has to contain the names because they're using the lookup table. And we probably need to have some scopes for this in case of anonymous structures. Some kind of scope we need to have. But really hacky, but it worked. C++ syntax is not great. Backend optimizer FE, I don't know what, or front end. Yeah, I want to write everything from scratch. I don't know how good it's gonna be, but I don't really care. I'm gonna try to make it as good as possible, and I'm definitely gonna work on this project a few years. So I want to make it as good as possible, but I'm really doing this for learning. That's why I'm doing this. So yeah, if I'm just using LLVM, I don't learn how to do optimization, which is really interesting. So yeah. STD variant didn't, okay. All right, let's add a type here. I'm gonna add a type for the structure. And I'm gonna use in big capital letters. So this is struct in capitals, because struct is a keyword. And then we need a struct member. So we both need a struct type and a struct member. All right. So the struct type is gonna have like a list of members. Thank you for following, Reno. So I'm just gonna have a list of members. I'm gonna say this is a list of struct members. And then this is gonna have a list node in order to make that work. So we need a list of members. Or not really, this is just a type. So the struct member has a list node. Each member has an offset and an alignment. Okay. And then we probably should have like is anonymous. Is that right spelled? Anonymous. It's anonymous. So it has a list node of this. So this is really just linked into the struct type. And each struct member has a struct member type. So it has a type, and this might again be just a struct type. That's fine. So a member can have a type, and if this is not an anonymous member, we are supposed to have a name. Yeah, so a strict member has a name. So we can probably use this one for checking if it's if it is an anonymous member. And I'm gonna bring it up there. So string name, and I want to store the token somewhere. So just down here I want to store the actual token. I don't know what this token is gonna point to. You kind of have this member here. Is the token gonna point here, here, or here? I don't know, maybe it's just gonna point to the strict keyword. We have to see. Some kind of token there. And the strict type has just a list of members. And probably this is gonna have an offset as well. Okay, let's just start with this and see where it takes us. And by the way, we need to parse member access as well. So this is supposed to parse a structure or union. This is going to return a type. I'm going to call it parse. I'm going to call it parse struct declaration. This is really struct or union, but it is basically the same thing. Parser. Yeah. So this is returning a type. And we should also be giving it if this is a structure or union. Let's think here. I'm gonna call this here. And we know what the type is. So maybe I'm gonna do this check in the actual function instead. So this is parsing a struct declaration. No. Oops. So whatever, I'm basically parsing this part, not the token. And this might be a variable, anonymous structure, or a type def, like this. So this type is going to go to the declaration. So I can say declaration type is equal to parse struct declaration, and this is not going to have like in some kind of initialization thing after this. I know this is really like how they do it in C. I don't like that. I think that's very hard to read. If you want to initialize something, maybe you can do it in here. Maybe you can initialize it in here. So after this is gonna stop. So it will not check for this initialization thing. In other words, it is just gonna push the declaration on the scope and return. On current scope, declaration, and return true, because we have parsed something correct. Yeah, parse struct declaration. So we should check the keyword to see if this is a structure or a union. Thank you for following AskCrack. Welcome to the stream. So we're grabbing the Lexer. And we're grabbing the current token. And we need to check if this token here is a keyword. And we need to check if this is equal to structure. like this. So that is keyword structure. And you're supposed to have this opening thing. So I'm gonna eat this keyword because I know this is correct. Eat this keyword. Parse struct declaration. So I'm gonna assume this has to be cool when I absolutely know this is either a structure or a union. I've already checked this. We can probably check it here as well, but we don't really need to do that. So let me just code something which I think will work. So after the structure, since we're consuming this, consume token, then this will point to the opening curly. So I'm gonna skip this token open curly, and then we're gonna skip the close curly somewhere down the line here. Are you planning to add a compile time execution? Yeah, I want. I don't know how to do that because I've never done it before. But it shouldn't be that hard. Isn't it basically just the same thing as I'm doing in the generator? Just as instead of writing these like move instructions, I'm making custom instructions that can be interpreted by the machine. It is very similar, I think. The only thing which I can think can be a problem is the objects. If I'm gonna allow pointers in there, which I probably am, then I need to check if that's gonna go out of bounds or something. So I need to store each object with a size. So there is not gonna need to be some logic there, I think. I don't know. But I believe this is gonna be very similar as this. It is just gonna be like a loop, like it's gonna read an instruction. If it is move, it's gonna perform the move. If it's add, it's gonna like add two variables together. It is not the interpreter which is hard, I think. It is how to structure things. Again, it is not the compiler which is hard, it is how to set up this stupid thing. Once you know exactly how this is supposed to look, it is so much simpler, I think. That's my opinion. I'm gonna take another coffee here. I have an iced coffee espresso macchiato. That's perfect. This is so good. It has more coffee taste and less sugar taste. So I'm not complaining about that. No, not as much as Jay. Not at all. I just want to be able to write, if I want to initialize some global variables at compile time, I can, for example, make a function which is doing that for me. So I can have some variable which is an array of U32, and if I want to compute this at compile time, I can make a function, and the compiler will run it, and it will fill in these members here. Because I can't remember when, but at least like 5 or 10 times I've had a need where I need to make some other program which is generating the output for me. If I had compile time execution, I can just make it here. I think it was, I can't remember where, but it's nice to have though. Screw coffee and mjöd. Mjöd is like a Viking drink, I think. Like Norse mythology. Yeah. Okay. Where were we? Yeah, so the open curly. We're gonna start here. Now we're gonna parse all these struct members. So now we have to think. At this point, the token pointer is pointing to the first entry in the member. So we might have two different cases here. We might either have an identifier or we might have a structure or a union keyword. So I'm going to say if it's an identifier and it is not this structure or union keyword, then we have some kind of tagged structure. Parse struct declaration. Let's make a new one for parse struct member. This is returning a struct member. Thank you for following Random Low. Random L. LD. Linker. Random linker. I'm gonna say the token is equal to current token using this lexer. And I'm just gonna have a while loop in here while inside these brackets, and I'm gonna check for members. So I'm gonna have some kind of while loop, and I want to check for this current token. So I'm gonna store the token first, and then I'm gonna do while token kind is not equal to token open close curly, and token is not on the file. So while this is true, we're just gonna keep iterating. And if we're having like an empty body here, we're skipping this one, and the token will then point to the ending one. So this will not happen, and like this will not happen. So then we're accessing the struct member, parse struct member. There we go. And I'm gonna add a member into this structure list. Where's my tree? So now I'm gonna add this structure, this struct member, into this list. So I'm gonna allocate the struct type first. I need to allocate a struct type here. And then I need to initialize this members list. This is really just a struct type. New structure. Let's call it struct type. Let's call it just structure because I'm using new pointer here. So I think that's the best name. So this is gonna make a new struct type, which is equal to new type, and the type is gonna be a structure. So I'm gonna add this type struct into the enum as well. So I have the types here, and we have basic, pointer, inferred, unknown, and structure, finally. So we're initializing this list members and returning the type. Sounds fair enough. We're gonna just add a type here. So new structure, we need to define this in the header file as well. So now this has the members list initialized. So we should be able to do list add last member list node and members. So this will add the member into the structure type. So this is good. And then we have to fix this parse struct member function. Yeah. So we're getting the current token. And we need to check if that one is... Where is my tree? There we go. Yeah, so we need to check if this is a structure keyword. So I'm gonna go if token kind is not equal identifier, I'm gonna error at token. Expecting either a tag or a struct union keyword. So that's if we're getting something like this. That's not allowed. So we're gonna say that. And then we check if is keyword token keyword struct. We're checking if it's not a keyword. So if it's not a structure and not a keyword, no, if it's not a structure and not a union, we're gonna parse this name. So this name here is a tag. So this new struct member has a tag. Let's allocate a struct member as well. Struct member this doesn't really, like when traversing a type, you don't need to know if things is a struct member. So we don't need to make this as a union member. We can just allocate this separately. So that's going to be what I'm going to do. Yeah, we're just going to return a member. So here, I'm going to allocate a new struct member. There we go. And then I can say member is anonymous is equal to false. This is false by default, so that's fine. I'm just going to say it for it to be explicit, so it's easier to see. So anonymous is false, and we then have a name. So I'm going to say name is equal to token name. I'm storing it there. Question is if we're going to set a token as well, if we're like going to report an error. I don't know. I think I'm going to set the... Because we don't... Yeah, we might have something else as well. I'm going to set the name. If it's an anonymous struct, you're going to set the token here as well. Token is equal to copy token. Like I have to check this later. Doesn't really matter, it's just for error reporting. But I should try to be consistent here. So this is if we have a non-anonymous structure, like a normal member. And it doesn't make sense to type def something inside a structure. I shouldn't be able to do like this. And then this has a scope only inside here. I don't see the point in doing this really. What do you think? I don't see the point in doing this. So then you can say like this has type AI. I think we're gonna not support that one. Yeah. So basically we're gonna expect a single colon. You can add it later if you need to. That's right. I agree. Okay, so if I have a member, which is not a structure or union, I'm going to parse the name, and we're going to skip the colon, which we're skipping this one. And then we can have either a structure, a union, or we can just have a type name here. So we have to parse a type if it's not a structure or union. So I have to just check here again. We're having the current token, and we're checking that one, so we can just update it here. Token is equal to skip token. So now I can check if keyword token no, keyword structure. Else if keyword is union, and then we just do else. And then we're going to parse a type. And does the type parser fail? This is parsing a type, and it returns, yeah, so that, I'm not sure if we're going to do this. This kind of have to return a type. So I think we're gonna just have the expecting a type, and so we don't need to care about it. So basically the member type is equal to parse type. And this does not do anything else than just parsing the type. So after this, if it is a member, we're gonna skip the semicolon. Skip token. Lexer token semicolon. Thank you for following. Thank you. Okay, so that's skipping the semicolon if it's this case there. And if it's a structure, we're gonna handle it here. This is also we could do this the same way as we do down here. So if it's either this or this, we can just parse structure union, because it's going to check it again. So I think we can have one of these. It's going to parse parse struct declaration. So it's going to go down here and parse this again. And now we need to think, is this going to work? Parsing a struct declaration, consuming a token, that is the keyword, allocating a new structure. This doesn't return anything. We're gonna return the type. So I'm going to return this structure type, which has the same matters as just a type. Let me double check that. Yeah, so it's in here. Probably we need to check if something is a structure or a union. So I'm gonna add a field for it. In the structure, we're gonna say is structure. So this is 1 if it's a structure, false if it's a union. So I should be able to say type is structure is equal to keyword is struct. All right, so now we know if it's a structure and it has a list of members, and that might be new structures or it might be something else. And if we have an anonymous structure, this will be true and it will not have a name. Hello Giuseppe, welcome to the stream. Hola. First I'm here, but it looks cool. Hi chat. Hello, welcome to the stream. Welcome. Nice to have you here. We're making a compiler, by the way. So now we need to support these scopes, but because I want to place things in the scope as well. So these kind of declarations here are really gonna exist 2 places. I guess this is simple if this is a simple search. So if I have a dot member, if I want to have like, let's use the capital word. So token A and test, and I'm removing this. Then I can just look at this token here. That's gonna give me a pointer to this structure. So I basically know this. And then I'm looking for, I'm just iterating over all the members and I'm comparing the word A. And we have a match here, so that's gonna give me the structure, this structure. And then I'm looking for the word test. And then I can just recurse in. So if I'm getting an anonymous structure, I can just recurse in and testing and checking it in this as well. So the allocation of the offsets will be very simple. Because I'm gonna just recursively call lookup in structure. Or like assign offset in structure or something. So this is gonna have an offset and this structure is gonna have an offset. The problem is when I'm adding this test here, how do I know this is a unique name? So if I have like an anonymous structure like this, how do I know that this hasn't been defined before? So then I need to go in here, I need to go in the parent scope and I need to iterate. I need to iterate down to the top level scope and iterating into all these anonymous things. Thank you for following. Or I need to iterate out until I'm getting a tagged structure like this. So if I'm gonna add this test variable, I need to first iterate over, I need to check it in the current scope. And since this is an anonymous structure, I need to go in the parent scope. So this is a tagged structure, which means I'm not going to recurse to the top level scope here. I'm going to stay in this one. And then I'm going to go over all the members. And then I need to recurse into all these substructures, which is anonymous. For each single time, and I'm actually checking the variables over and over again. So I think I'm going to be using scopes instead. So I have like a scope for, like this A structure is having a scope. And when I'm opening a new tagged structure is going to make a new scope, and that has a pointer to the parent. And we don't really need to point to the childs because we're not going to check the childs. We're not going to access the members. We're going to access the members by just iterating the structure. That's just for just checking if a member is unique. Have you checked out the work that Jonathan Blow has done in his language J? Yeah, I've checked it out. He's a really good programmer. So I watched this video on how to make programming language parsers. So he was the one who told me, or like, how you should do the parser. But I believe he is doing some tree manipulation on the way up on the expressions, while I'm doing it on the way down. I'm just doing like a conditional recursion. So that was really nice that he made that video. That made it really like much simpler. You go up as long as they're anonymous. I won't be opening a new scope for anonymous structures. Yeah, that's right. I won't be. The question is, should I just iterate, or should I make a new scope? Actually a scope. I probably will be having the scope, because then it's going to be faster to access these variables. I'm going to assign the offsets by iterating the members, because I kind of have to know the structure of the graph to do that. But when I'm like having a dot expression, I'm going to look up in the scope. I think it's faster by using scopes. And then I can also implement the hash table. So if this structure is going to be very big, like look at Linux, look at the TCB in Linux. That's, oh my god, that's big. The TCB is the thread control block, which stores all the information about the thread. And that's many lines of code, just a structure. So I'm thinking maybe a hash table on this structure later. So I'm gonna make a scope for this. For a name structure, create a new scope. What is point of struct? That's not really a point in doing that. Anonymous structures are usually placed inside a union. Okay, so we're gonna open a new scope. Let's see if we can use the normal scope we have here. This has a list of functions, variables, types, and it has a list node and parent. So we don't really need this part. We don't really need this one. We don't need that one, and we don't need this. We basically need a pointer. We need a list of all the struct members which are in there, and they should have a unique name, so it should be doable. We should be able to replace it with a hash table. I'm gonna make a new kind of scope for this struct member. I'm gonna call it a struct scope. Let's add it in a type def first. We need a pointer to the parent. This is used when we want to check if a variable already exists. Or do we? Yeah, and we kind of need to have the parent here. Not because we need to look it up, because we're only going to look up a variable in the current scope anyway. But because we're actually recursing. When we build this kind of structure, we need to allocate more struct scopes. And when we exit a tagged structure, we need to replace the current scope with the parent scope. So we need to keep this kind of parent. That's going to make it simpler. So this is having a list of, I'm just going to say members. And that's it. So this might be replaced with hash table later. And each strict type has a scope. Is that right? This is really only like non-anonymous stuff. So I'm wondering where I'm gonna place this current scope. Am I gonna place it here or in a struct member? We kind of need like the top level scope is also gonna have it. So probably this struct type should know if this is an anonymous structure. I can just assign a variable here with the same value as here. And then we can have the scope here. Isn't this strict scope and statement scope the same thing? Kind of the same thing, but this is smaller. And then the list is going to contain different stuff. This is going to contain a list of members. And while the other thing is containing a list of declarations. So in order to avoid confusion, I want to make a different scope for that. Okay, so this has a scope. We can just populate this scope if it is a anonymous structure. Okay, I'm gonna go with this. We also need to track the current structure scope. So I'm gonna go to the parser and we're gonna track the current struct scope. Yeah, I think that's good. That's very good. And we're going to assert that this current struct scope is going to be 0 when exiting the declaration. So when actually exiting this one, we're going to assert that the parser current struct scope is equal to 0. And this is 0 by default because this is callocked. So what I need to do, I need to open a new struct scope when I'm having a non-anonymous structure. So if I'm having some kind of tagged structure, I'm going to open a new scope. And that's going to be placed on the current scope. And if I'm opening a new one, I'm going to have a pointer to the previous one. Current scope, let's make an allocator for that. New struct scope. It has a list of members. We're going to initialize this list. Okay, so initialize the list and we are returning the struct scope. This is kind of the same thing, so I'm gonna group them together. New struct scope. I don't know if we're gonna need it, but I'm gonna make 2 functions for entering and exiting a struct scope. Enter struct scope, and we're going to give it to parser. This is just going to be a void. So exit struct scope. So here I'm gonna say, we're gonna assert that the parser current scope parent is something, because we're gonna replace the current scope with the parent. Okay, does this make sense? And this if this is happening, it's like we have to fix the compiler. If we're gonna enter a new scope, we're gonna first allocate it. And then we're saying scope parent is equal to parser current struct scope. If this is 0, that's fine. Then it means that this will point to 0, which is basically happening in the first case, when I'm opening the first scope. And then we say the parser current scope is equal to scope. Okay, so that's entering and exiting a scope. Simple. Parse the struct declaration. So I know the first one is, when I'm parsing the top level one, I know that's a tagged structure. So I kind of know the first one is going to have a new scope. So when I'm parsing a structure, I need to know if this is going to open a new scope. Here we go. I need to know if the struct type, which I'm allocating here, is going to open a new scope. So either I can give it the scope. I don't know if I'm going to give it the scope. I think I'm going to give it a parameter. Is anonymous. So if this is not an anonymous, I'm going to say is tagged. No, I'm going to say anonymous. I'm going to use the same word all over. If not is anonymous, this is a this is a tag structure, so we have to open a new scope. So I'm gonna say enter struct scope with a parser. And this is going to also return the current, it's going to return a new scope. And I'm not doing that, so I have to return it as well. And then we're going to link this new scope with the type. So we're going to say type scope is equal to enter a new scope. So if the type pointer is something which is not 0, we know this is a tagged structure which has a scope. So I can look up in this table instead. And this is going to have like declarations. Yes, I can just search the name there. So I basically need 2 list members here, which is a little bit stupid. I need one for placing it in the actual tree and one for making the lookup faster. Yeah. So we won't be able to use global variables in struct to initialize fields. I will be able to do that. I want to be able to do that. But I don't see why this is going to prevent me from doing that. Yeah. Okay. So now I have a new scope. And it should always have a scope. So when I'm making some kind of new member, I should like assert that I have the scope. This is going to be open the first time anyway. And this needs the anonymous. So what if I have this? This is not an anonymous structure. This is kind of an anonymous. With anonymous, I mean something like this. This is a tagged. I don't know like what the word I'm gonna be using for that. This is gonna push a declaration, and this is not an anonymous function. So that's gonna be false. So that will open a new scope. And when I'm done, I'm gonna exit the scope. Exit struct scope. Okay. So we have to do one more change. We have to, when we add stuff, I'm gonna add a member to the list node, and we're gonna add this last in the scope. So this will be a member scope node, and it's gonna add this to the scope. So that'll be like parser current struct scope members. We can replace this with a function call later, but I think this is fine for now. So this will happen anyway, but not every structure is going to open a new scope. And here I can just assert that it's not on the current scope yet. So we're going to check the current scope first. Let's make two functions. Thank you for following, Swati. Welcome to the stream. I'm gonna push a struct member on current scope. This is gonna take in the struct member and the parser. And then I'm just gonna say list, list that last member scope node to the parser current scope members. And then I'm gonna make a bool. I'm gonna check if this already exists. What am I gonna call it? Is does struct member exist? Okay, so this is only going to check in the current scope, since we're not going to recurse up because each single scope is a new tag. So since I have to go through the tag to get that element. So it's, yeah. Struct member. And this is gonna push. This is gonna push all. Like, this is gonna push all, like, named members. It is not gonna push. It is just gonna push the named members. Okay, yeah. It's only gonna push the named members. So when I'm accessing a member here, that will have a name. So I'm gonna assert that the name is not anonymous. If this member is anonymous, I'm not gonna add it. So I have to check, like, if member is anonymous. Oops. we are not pushing Okay, thank you for following. So if it's an anonymous, we're gonna just return. And this is the scope node. So we're certain that it's a not anonymous structure, and then we're gonna do string compare. We're gonna compare the address of member name. This is the same member though. I'm gonna call this new member. I'm gonna call this scope member. So if the scope member is anonymous, we're gonna assert false, and then we're checking if the member name is equal to the scope member name. And if this is true, we're going to return true. So we're just going through everything, and if we don't get a match, we're going to return false. So before I'm adding this, I can call push direct member on current scope, member parser. And if does direct member exist, we're going to give an error on the member token. We don't have a member token. I have to error some kind of member. Like here we know where that was defined as well. Okay, when I parse this thing, I'm copying the token in case this is an. All right. So since I'm, I need to check if this is an anonymous thing. I'm gonna assume anonymous. I'm gonna make a new member, and we're gonna assume this is anonymous. And if we have some kind of identifier, which is not a keyword, we're gonna set the anonymous to false. So if this is happening without this being happening, it is gonna have anonymous equal to true. So this means that this is only gonna be added to the list, as we see here, if the anonymous is false. So basically, if I'm having an error, if this does exist before, I can use this token because it's pointing to something valid. So I'm gonna fix the error message later. Doesn't really matter now. Okay. So I think this is gonna be able to parse a structure or a union. Let's see. Copy token needs not a lexer, it needs a token. So this needs the token instead. skip token 509. This needs elixir. Just being a little bit quick here. Implicit declaration of parse direct declaration. Of course. So we need to call this parse direct declaration from the struct member if it's going to access that. So we need to define it here as well. Thank you for following Manasb. Let's do it like this. Yeah, Manasb. Yeah, parse direct declaration needs to know if it's anonymous. So when I'm calling a strict declaration here, I need to know if this is anonymous. So you can just give it, if this is anonymous, and return member. 102 list in its scope members. Okay, so this is wrong. We're not allowed to write this. This should work. Everything here should work. Assertion parser current scope parent failed. Okay, let's see if we're opening a new scope here. Wait a second. If this is anonymous, it's going to open a new scope. We have to exit it if it's anonymous as well. If it's anonymous. Doesn't that make sense? Parent scope failed. If not anonymous. It's still, it is still complaining. Okay. It is exiting a new, it's entering a new scope and it's exiting a new scope. No, it's not going to assert this. It is going to assert that we have a current scope. It can't exit the current scope if it doesn't have a current scope. So this is it is just going to check. It's just going to check if we have a valid one. If we have, it's going to set that to the parent. So the parent might be 0. The parent is in fact in this case 0, but that's going to make the current scope 0, and then the next time it's going to fail. So parser push declaration declaration type not handled. Thank you for following. So this is when I push a declaration on the current scope, not the structure scope, but the actual declaration scope. So it says the declaration type is not handled. This is because when I'm parsing this declaration, I have to set if this is a variable declaration or a type declaration. So that's really being determined by this is type def. So I'm setting is type def equal to the double colon. So if I'm having a double colon, it's a type def. And I'm setting the declaration kind of all over the place. So I have to do I have to do declaration kind is equal to, if this is a type def, this is going to be declaration type. Otherwise, it's going to give me the declaration variable. So now that should be handled. And then we have expecting God identifier. What is it expecting? Expecting colon, but God identifier. So we're failing to move the pointer somewhere. Parse struct declaration, that's fine. Parse structure member. Yeah, so we're getting the current token. So the current token, if that is if the current token is an identifier and it's not structure or union, we're gonna first skip that current token. First skip the identifier. So that'll actually skip this A, and then it's gonna try to skip the colon. So this is test U32. So up until this place, I'm only entering structures. So here I'm starting to exit the structures. So if I'm getting, for example, this one, it shouldn't recurse anymore. So I think I'm failing to update this token here. So after I'm parsing the struct member, I have to update the token. Token lexer. There we go. Fuck. Struct declaration is defined before. Okay, so this is working. This is defined before. It's defined right here. If I had a tag here, let's give it a tag. That should work. Dang it. Oh, A is defined before. A is defined up here. If I'm giving it an in, okay, this is working. Yeah, now it's coming down here. So it actually can parse this now, which is very cool. We can parse this kind of structure. And it seems like the scopes are working very well. It is much faster. The only drawback is I'm using a little bit more space, because each struct member has to have 2 list nodes, which is actually 16 bytes of memory. But it's not like I'm not using that many structures, so I guess it's fine. And if I'm using like a struct reference, I'm only going to copy the pointer. So it's not duplicating any memory. Unless I'm having like parameters to structures, then I guess I need to copy the entire thing. But I guess it's fine anyway. Thank you, Nasaibot. Thank you. Compiler for what? This is a compiler for something like C. It's not going to be just like C though. Luxury. I like the name Luxury. It's easy for 9.99 a month. Yeah. Just git clone. Therefore it must be good. Hash table and an oriented list is the usual thing to use for that. Yeah, definitely. I'm going to be using a hash table later. I'm just using a list because it's a little bit simpler. So until I'm figuring out this language, I'm going to use lists. And then I'm going to replace it with a hash table later. Okay. So still we're only getting this. So we have an assembler message, space repeat 0 count ignored. Output S76. Oh, token is 0. Token is 0. Yeah, so we're allocating a new, this is a member, that's a variable which is global, and for some reason the typer doesn't take that. I don't know why. We have to go into the typer and actually type this thing. So this basically has a size 0. I'm gonna delete this. Let's try to print this kind of structure. So how do we want to print it? I want to have like a new structure. It's gonna tell if it's anonymous and it's gonna list the members. That's simple. Tree printer. As long as you're under 1,000 entries, yeah. So it's probably gonna be fine for anything. But I'm gonna replace it later. I guess I remember something that Jonathan was saying, like list is actually faster in some cases because the memory footprint is gonna be smaller. So it depends on the size, like the number of elements. In some cases, lists are actually faster because it's gonna make more hits in the cache. It depends. Because if I'm gonna allocate a hash table, I need to allocate like a lot of pointers for these linked lists in case I have collisions. And that's gonna take up a lot of memory. But I don't know. It's just something that I remembered. We'll have to see about that. Yeah. Okay, let's print it really quick. This is printing a scope. Where's the scope? That's here. And I'm printing the variables after. And then I'm printing the typedef. This is the type, that's a stupid comment. So that's gonna go in here. I'm gonna print typedef. I'm making a new typedef. Yeah, this is correct. And then I'm printing the type after. So I have to change this type printer to support structures. So if this is a case structure, I'm gonna just call print struct. I'm just gonna do it in here. So we have a struct. Okay. So this is the member, and we can do like struct, and we can give it a name as well. Or we can say if this is anonymous. So I'm gonna say something like if struct. We don't really have anonymous here, so I'm gonna just use a scope. If the struct has a scope, it's gonna be mapping between a type and which is a new struct. Okay, I guess I can do it like this. Anonymous. Yeah, I'm gonna just do it. So if it has a scope, it is nothing. Otherwise, I'm gonna say anonymous. So this is printing the structure, and I'm gonna go in and print all the structure members. You know what? I'm gonna print it in a separate function. I think that's cleaner. Print struct Then I'm going to copy this. Because this is actually going to be a big function. Like bigger than this. So I'm going to call print structure with a type. And we're going to iterate through all these list members. List iterates. And members this is a list node. We have to be careful because we're having one list node which is for just the regular members list, and then we have a scope node which is for the scope list. So we're going to be using list node here. And then we have a member. So we want to print member, member, member. We want to check if something is the last member. And I want to save the indentation of the struct print. So indentation plus plus. We're going to indentate after the structure. And then we remove the indentation afterwards. Minus, minus. And if we check if something is the last element. So if iterator next is equal to the address of struct members, I really need to make a function for this. Like is last in list or something. If it is last, we're gonna paint the mask here anyway. So mask struct indent is equal to true. If this is the last one, we're gonna set the struct indentation to false. Then it's gonna stop to print those vertical lines. And at the very end, we're gonna stop it anyway. Because if we don't have any, if we don't have any members here, this will still be true. So we have to clear it manually. And for each member, we're gonna print indentation print struct member. Let's print the member on the same line. We might do something different later, but I'm gonna start by doing this. We don't know if it's a member though. I'm just gonna print struct member. This is a struct member. And I'm gonna save the member indentation. Indentation plus plus. Down here. And then we do indented print name. This is happening if it has a name. So I'm gonna check if member is anonymous, is false. It's gonna do this. Oh, Hero said I have to check it. Like, I'm not getting any sound. I don't know why I'm not getting any sound here. That's weird. But thank you very much for the raid. Thank you very much. You raided me yesterday as well. I'm very thankful for that. Did you have a nice stream? How was your stream? You hashed the key. Yeah, that's essentially it. Language. This is a custom language. easy to build a compiler is like a hammer to build a car. Yeah, so we're making a compiler for the new ones. We're just trying to make a new language. So I have been streaming this for 3 days, and now it can compile like pointers and types and very simple type inference. So now we're gonna try to support structures. So the previous streams are on the YouTube channel, and they should start from like 0, just setting up the project. It's like 10-hour streams every day, so 30 hours, I think. So that's what we're doing. Is that much? All right. So now we're trying to make these structures work. We're gonna be able to generate code for these structures, and like the member access and increment the address with the correct size and stuff like that. So that's gonna be interesting. And yeah, so right now we're just trying to print this. We're gonna represent this in some kind of fashion like here. So that's what I'm doing. But thank you very much for the raid. That's very nice of you. Okay, so print structure, I'm printing the name. And then the print name, and then it has to have a type in any case. So I'm not sure how I'm gonna write it. Type, we can just do indented print type, and then we print the type. Member type, assert type. So this is gonna like have an indentation. Indentation plus, indentation minus. I'm doing this manually because I want to know what's going on. Well, I'm doing this 2 times. Okay, I'm doing indentation plus there. All right, so that's a strict member. It has a name and a mapping between a name and a type. We might simplify this a little bit. Let's just see how it is now. It's interesting when you're using just print somewhere. Oops. So you're having a type def. So token is being type defed to this, which is a structure of one struct member. If it is an anonymous structure, it should also add these anonymous struct members. Struct. That's not happening. Struct member data. I'm probably not recursing into this thing. So for each struct member, I have to check if that is a new structure. Indentation plus, minus. I don't understand why it should have so many. Like, this is one structure with a struct member called A, and this has a type struct. So I don't know if I'm gonna print the type here, because the struct member is already here. So I'm gonna remove the type. So I'm gonna delete this, and we're not gonna indent the print type. So the struct member is name, and that name is a structure again, which has one struct member, which is data 4 bytes. So we're getting this, and it stops suddenly. Oh, if list next is equal to struct members. There we go. I don't know what happened there. I don't know. It shouldn't be doing anything. Oh, I'm saying that each iterator next is equal to something. Fuck. So this is actually making it the last member. So I have to do equal here, like a comparison instead. Built-in dictionaries. Like C is lacking some features, but you can just make them yourself. And that's actually a nice thing, I think. C is not a pain. Like, to be honest, C is... Everybody thinks that C is just such a pain. Like, we have a school project at school, which we're gonna make an elevator talk over the internet to other elevators. So basically, you're pressing some kind of button, and some elevator are gonna take the order. Like in any case, if it's a power down or like any case, the order should be taken. And yeah, you won't believe like what solution students are doing there. They're using so difficult solution with like ring buffer and master slave backup master. So complicated, like multiple thousand lines for that simple project. And they also like say that, oh, you're programming in C, you're not gonna be able to do it because it's so difficult. Like, I think people has this misconception about C. I wrote the elevator project for like a few weeks ago, and it was like 300 lines of code. Just UDP broadcast. So, like, I think there is a misconception about C. That is so hard. Like, some things are harder to do in C than other languages. Yeah, I don't know. Curly braces. Beautiful ass. Yeah, this is cool. I like actually how this is looking. So this is actually the first run. I'm retyping the tree here. So this entire thing is a new type. So I should actually be coloring this entire thing with a type. With green. I don't know how that's gonna look. But I'm gonna apply this. I want to make this very small because I'm gonna apply this multiple places there. Thank you for following, Fakor. Welcome to the stream. But I seem to get it right though. And I seem to handle everything. So I think we can start actually doing some fun things with this, these structures. Yeah. Let's just paint them with green instead. Yeah, so I'm gonna do indented print. I'm doing colored print on all of these. And I'm gonna say color green. Oops. There we go. So everything you see which is green is just a type. It denotes a type. So now we have to go through this entire thing in the typing stage, and we have to assign an offset to each of these members. So each member is going to have an offset from the base structure, which is, it doesn't really matter. It doesn't matter if that is a structure, if that is an anonymous structure or just a structure. So this tag or this member is going to have an offset from the parent structure. They're the one right adjacent to it. So we're going to go through the tree and we're going to type everything. The question is, are we really going to do that? Are we going to give it the base from the last tagged structure? I think actually, since we're using the hash table for the lookup, I think we have to, this is gonna have the offset from A instead. Because this one, this structure, so this is a tagged structure, so this is gonna have a scope, which is gonna contain the test U32, which is up here. So if I'm searching something like token A, that is going to give me this structure here somehow. And from this structure, I know the scope. So if I'm accessing a member here, which happens to be test, I will need to be able to look up this in that scope. So this test needs to have an offset from where I'm looking it up. If I was just iterating here, I can just check if this was an anonymous structure, go into this one and do offset plus equals something. And I go into a new one because I have an anonymous structure there and do offset plus something. But I think I'm going to go with the first thing here. See at high school. I didn't program anything before university. I think this was like the magic thing, because I remember so well that other students at, I don't know what it's called, like high school, like before university. It is like 3 years in Norway before university, and someone had like programming subjects there. And I just imagine they were very difficult. Like programming was this weird thing. I don't know. You can use C for everything, that's right. Linux is built using C. But did you read the Dragon book? I did not read the Dragon book. I don't think I read any book. My personal thought is that books are very long, and there are better ways of learning than just reading books. So I think also that if you just attempt to do something yourself, it is not going to be that efficient. So you have kind of to take inspiration from others. But I guess that trying out yourself is better than just reading books. You can't really learn how to make a compiler without making one. That's my thought on it. Okay, we're gonna fix the offsets first, and then we're gonna add support for dot expressions. So like token dot something. So now we're going to go into the typer, and we should be typing all these types. And I also want to make the typer a little bit different first. Let's think a little bit. I'm gonna delete this. Because as the typer is now, the type inference is a little bit picky. It has to be declared before. And I know there's a better way of like restructuring this tree. I'm just thinking if I want to support multiple passes. If this type program is going to have a loop and it's going to type the code unit. So let's, in the typer, this is the object which is passed around. So I'm passing this typer object around, and this can probably have like 2 members. So type resolved and unresolved types. So if I'm adding those 2 members, I can say something like while typer unresolved types and type resolved, I do this. So I'm basically calling this type code unit as long as I have unresolved types and I'm still resolving any types. When this exits, any, like either this one or this one is failing. And if I then have unresolved types, I'm gonna error. Typer failed. This is certainly not how type inference work, and it will be very slow, but it's gonna, I think it's gonna do the job. But then we have to support that in, we have to go through this code and just see how that's gonna change things. So if we have unresolved types, we have typer failed and exits. All right. So we have to detect if we're having any untyped nodes or structures or something like that. And that's more specifically happening if we're having infer type. So if I'm writing data equals test and test is defined here, this can't be determined because it first has to know what test is. So it's first going to go down here and try to figure out what type the test has, and it is resolving this type, so it will still do this loop again. And then it's going to go up here, and then it knows the value. So type code unit is going to just type the top level scope. So we're resolving the types first. This is where I'm gonna fix the structure. So we'll have like type pointer, type unknown. If this is a type structure, I want to compute the offset here because I know all the members. I know the type of all the members. So I know their size as well. Thank you for following Stryhacks. Yeah, resolve type. It's not going to do anything, it's just going to ask for resolving a type. And it's giving the typer. So if it resolves a type, if it does this, it is going to mark the typer as new type is resolved. Declaration function, okay. So resolve type, it's gonna go in here. Let me use a switcher instead. Thank you for following. Type unknown, pointer inferred, and we have unknown. Type structure. So pointer, then we're just recursing down again, so we can't resolve anything here. The pointer is still going to be a pointer, it's not going to resolve anything. And in case we have an unknown thing, I'm going to place it in here. I'm not sure if I like having that much thing in there. So that's an unknown thing. I'm gonna resolve that up here. I'm gonna delete this. I'm gonna do a function call instead. So resolve unknown type. And this is returning the type. So now we have to think, if this is unknown, it's not gonna set anything. So we're just gonna return that one. And then we have error. Okay, yeah. And then we have the default case. This is in a typer. Unknown type, kind. Okay, so we have an unknown type kind. So we're supposed to handle everything. If it's inferred, if the type is inferred, then okay, so we resolve a type. Let's just keep this waiting a little bit. I think I'm handling the inferred thing in the binary expression, because this is where I have an assign. I have to fix this. This is too many arrows for my taste. If this is inferred, I'm accessing the declaration here. I'm setting the declaration type. So I don't know if I'm setting things first. Okay, if I resolve this one, so if I have a declaration, look up in the current scope. If this is an unknown type, I'm gonna try to resolve it. So I'm first saving the string, which is unknown token name, typer name, and if I find a declaration, I'm gonna assert this and return the declaration type. And here I'm gonna set type resolved equal true. The reason I have to mark this as type resolved is that if I'm having this kind of thing, it will kind of just go in a loop. So on each iteration here, I will not resolve anything. And then this will be false, and then I'm gonna exit, and then I'm gonna have this typer failed. So this kind of doesn't work. And then we have to print where that happens. And then we type a function. And it makes sense to have the resolve type first. Wait a second, unknown type. This is an unknown type. If I have a type def, so unknown types are basically if I'm having a variable which is a token. This is unknown because it doesn't know what this is. So this might be defined up here. So token might be a U32, or this might be something else. So this might be an IP. I'm using the same examples all the time. This might be an IPv4, and token can't resolve this one because it doesn't know what an IPv4 is. It's gonna find it down here. So in some cases, even though I'm looking up the declaration here and have a declaration for this, I have to check if this type is unknown. If this type is unknown, or if that type is unknown, I can't do that. Yeah. So if it's an unknown type, I have to assert that if I have a declaration, then I need to check if that declaration is valid. So if declaration kind is not unknown, then I'm going to return this, and I'm saying that I'm resolving a type. Otherwise, I'm just returning the type I'm given. I'm not resolving anything. Okay, that should work. That won't work yet. And typing a function, it's first typing a scope, and then we have this crazy thing like enter scope, stupid thing. Because we have function scope, which is just a function argument list. But we're not doing anything in here. I'm gonna go up here, type statement. It's just doing this. Type loop statement is just typing scope and expressions and stuff like that. Type statement. Okay, so here I'm typing a call expression. I'm only calling into type expression here. I should probably be setting so here I have an error. I had to remove this because I was getting errors on the printf, because printf is not defined in this file if I'm printing something. Okay. Thank you for following. If I'm doing this, I still have to do like type conversions and stuff like that. But just to make it simple, I'm saying expression type is equal to function return type. So here I'm gonna say type result is equal to true. In any case, like I kind of have to set it there. Okay, and then we have the primary. This is also supposed to be simple. If I have a primary identifier, I'm gonna look it up in the current scope. And if that declaration has some kind of valid identifier, here we should assert that it has a declaration. Assert that the declaration has a type. This is supposed to happen. Every single declaration should have a type, because a declaration is basically a mapping between a name and a type. So we have type kind. So we have basic, inferred. If this is inferred, it kind of doesn't work. If it's either inferred or unknown, it doesn't work. If the declaration is unknown, which is the case here. So I'm going to make a helper function for it, like is is a valid type. This is going to return if type kind is not equal to type unknown, and type kind is not equal to type inferred. Okay, so I'm checking if this is a valid type. Declaration. Then I'm doing this. Thank you for following. So I'm resetting primary declaration equal declaration and doing this, and then we're going to resolve a type. Type resolved. Else we have an unresolved type. And then we delete this, and we have to set it by default to some special thing. So by default, we're gonna assume that everything is it doesn't have any unresolved. It doesn't have. This is supposed to be false because it can't resolve a type before it's being called. Type resolved is equal to false. We're setting both to false. So it doesn't have any unresolved types, and it doesn't have a type resolved. This is type resolved. Otherwise, we have typer unresolved types. As long as we have unresolved types, yeah, okay, so as long as both are being true. Okay, so here we're setting unresolved types to true. That's fine. Type call expression. We're not gonna handle this one, I think. Yeah, we're just not gonna care about the call. I don't think that's gonna introduce any issues. Here we're resolving something. Typer resolved is equal to true. Pointer, this is if we have a string. So here we're also resolving some kind of type. Okay, and then we have unary. Then we're checking what this is pointing to. This is the address of. This is an expression. So if I have something like variable, and variable is defined as a token, and it doesn't find a token because this is defined as something else. So the token has either an yeah, okay, so if it's gonna first type the expression, it's gonna typeset this one. Which is a primary expression. And it doesn't resolve this before it can be resolved. So we can't really resolve anything here if the unary operand is not resolved. So I'm gonna do if unary operand type is equal to 0, if it doesn't have a type, I'm gonna set typer unresolved type is equal to true. and return. And if this is happening, like if I have a new unary, I'm gonna do it down here. If the unary operand type are already being set, I'm gonna just return, because this might take multiple passes. I'm gonna assert that as well. So if the unary operand type is already being set, it's gonna return. It is not gonna resolve any new types. And then you type the expression, and then you check if it has a new result type. Yeah. And this might also have multiple passes. So I'm gonna check if expression, here we're setting the expression type. This is really not the unary type. This is the expression type. If expression type, return. So if the expression doesn't have a type, we have to look at the primary and try to figure out what that is. What tool are you using to outline in a term? This is a custom program. So this is something we just wrote. It is just normal C code. Printing. Yeah, okay, so we're left with the binary expression, which is a little bit, this is where most of the things is happening. So before we're typing this, we're gonna check if the expression actually have an unresolved type. This can be done before anything. If expression type, return. And then you type expression again, and this, if this is a new expression. So that'll, like, it doesn't matter if this left-hand side has been typed or not. It is just going to return. So here we're doing the type inference. And we're not looking up anything. So if the binary left is inferred, no, if the, this is a mess. If an expression is an inferred, if an expression has an inferred type, I'm gonna make a function for figuring out that. Binary left kind, this is an expression really, which is the primary. Yes, I'm gonna track if an expression is an inferred type, which is just a primary expression. Bool is inferred. It's gonna take in an expression, and this will return if expression kind equals expression primary and expression kind, no, expression primary kind equal primary identifier and expression, yeah, if that's a primary identifier, we're gonna do an if statement first. So if that's true, we're gonna assert the declaration. So primary declaration. So this is supposed to be true. It's supposed to have a declaration. And this is a pointer. So that value is supposed to be something. If expression primary declaration we're asserting the type as well. We're going to assert declaration and we're going to assert that it has a type. And then we're checking if type kind is equal to inferred. And false. So this will just check if a type is inferred. So I can replace everything with, I just want to check if the binary left is inferred. If this is true, I need to check if the binary right has a type, because I'm asserting that this has a type. If the binary right doesn't have a type, I'm gonna quit, because I can't really do this if I don't know the type yet. And we have to support the minus as well, by the way. So we're gonna check if binary right type is equal to 0, we're gonna return, and we're gonna set the type error and result types to true. If the right has a type, then we're going to assign a new type to the declaration. So we're saying that binary left primary declaration type is equal to binary right type, and binary left type is equal to binary right type. All right, so this is going to handle the inference. Left-hand side. If not, we return. Thank you for following. Looks cool, thank you very much. So what language is this a compiler for? This is a custom language. We're gonna make it now. What is not needed if only expressions are allowed? Opinion about Yoda conditions. I don't know what that is. Okay, I understand. So this is sort of happening. This is returning. So if it arrives here, both the right hand side and left hand side has a type. So we should assert. Actually, we should assert it here. There we go. So I'm asserting a little bit too much, but that's very, like, it sucks when you have like a segmentation fault and doesn't know where it is. So these assert statements help with determining where the segmentation fault is, if it occurs. Look up in scope. This doesn't really do anything. And then we have enter, exit, and so on. So I think we're done. I think we can test if this is working. Let's just double check. If the expression has a type, we return. If it is inferred, do this. Probably we should fix this part. I don't really care. Type unary expression. I'm gonna check if this is a type first. And then we type the sub-expression, and if that doesn't give any type, we return 0. We also have the case here when if the binary is not inferred, so we have like an else here. If the binary is not inferred, and the binary left type is equal to 0, then we return. Okay. If the right-hand side is failing to type, though, we're going to handle that here as well. So if binary okay, so I think that's tracking everything. Here we're checking if the unary type is 0, then we return. Assert. This doesn't really make sense because we're checking it in the if statement. Then we're filling in a type. This can go at the very top. Yeah, this is just a primary expression. Type call. And like this, yeah, we're just ignoring calls. So the only thing which is missing now is the unknown. And if it's an unknown type, it is going to check up if the declaration is known. So if the declaration is still unknown, it's gonna fail. Actually, I want to do it like this, because it's supposed to do this. To exit it. Oops. What happened there? There we go. Yeah. So if this is equal to unknown, or actually I'm gonna say if, I'm gonna be a little bit more generic. I'm gonna say if is inferred, I'm gonna say is valid type. So this is to the right here. So if the declaration type is a valid type, if declaration type, you're gonna resolve it here. I'm gonna do this instead. It was actually okay. Otherwise, we're just gonna say unresolved is equal to true and return. Unresolved type. I think we can try it now. So I'm gonna run this, and we have some problems. Implicit declaration of inferred. 96. 96 is inferred. All right, so I haven't defined this. We're missing assert. Or we're missing assert here in the tree. And then we have isValid type. So this is returning a bool. So I'm gonna return a bool. Assert 200 typer. There we go. So we have to fix the program first. Let's check if this is working. I'm gonna print data, which should have a value. Oops. And then I'm gonna print test. Okay, so we have an unknown type kind. I think that's the structure. I'm not sure. Typer unknown type kind. We're also printing what kind of type it is. So this is a basic. If we have a basic type, okay, so we have to handle basic types as well. Type basic. I think for basic types, I'm gonna so basic types I'm gonna just ignore. The only place that I'm using basic types is just by using this type table. And I know this is being completely typed. So I can just ignore basic types, I think. Assertion expression primary declaration failed. This is in tree. Assertion. This is strange. It seems that I'm having an assertion while I'm printing this. Or I'm probably done here. I don't know why this is happening though. Well, I'm having this weird print. Expression primary declaration in tree. But if you don't start using a debugger, I actually tried to do that yesterday. But it isn't as simple as it seems. I probably should. Thank you for following int82. Constant indicator of a variable. Constant is equal to variable. Where? And assign a constant. So you open the browser. Yeah. All right. So we're getting this assert failure. So the declaration which we're trying to find. Okay, so let's print what declaration this actually is. I feel it's some of this type devs thing that is just does not defer. It's not defined. Expression primary. Okay, we're checking if I is inferred. What the hell? The declaration fails, so it doesn't have a declaration. That's very interesting. The primary doesn't have a declaration. Doesn't even have a declaration. Yeah, so when we're calling this function with the binary left, so the binary left doesn't have a declaration. I'm actually going to use a name instead. So I want to print where this is happening, but I can't really use the name. So I'm going to be replacing this with that name. I think I can use that one. So this should tell me what primary expression I'm using here. So I'm checking if test is inferred, and then it fails. So the thing I'm checking test. I'm checking if the variable test is inferred. Like, how is the tree looking like? We haven't inferred on both the data and the test. So the declaration maps a type. Okay, I'm gonna see if we are resolving this primary expression first. So whenever I'm resolving this primary expression, this. So this is not working. I'm not resolving this if that is not a valid type. The declaration is not a valid type. All right. So I think yeah, I'm looking up the declaration. I'm gonna fill in the declaration in any case. The thing I'm not gonna fill in is the actual type. So the expression type can't be filled in, but this can go outside here. So I can link the declaration to the primary expression anyway. I can do that. I should do that. And then this is holding a pointer. Yeah, because the declaration is always known. But I don't want to do this if it is a primary identifier. I probably don't want to do this if it's already declared. So we can probably check if primary, if primary declaration is equal to 0, then you're figuring out the declaration. And then you assert that the declaration has a type, and if it's a valid type, then you fill in this. Whoops. What the hell? Oh, now this is inside. Then I'm gonna do it here instead. I need a declaration. So here I can be using the primary declaration instead. Typer failed. Okay. So the typer is failing. So let's print exactly what went wrong. I want to print the unresolved types and type resolved. Do I have a Boolean value? Can I print a Boolean? print bool C. Okay, it doesn't have it. That's fine. So I'm gonna just go with decimal. Okay, so unresolved type is 1 and type resolved is 0. It doesn't resolve a type and still there are unresolved types. So I'm setting unresolved types to true somewhere. Thank you for following. Welcome to the stream. Yeah, I could use that. That's probably better. Yeah. So that's true. Thank you for following, guys. Thank you so much. There we go. So true and unresolved types. So somewhere I'm setting the unresolved types to true, which is happening. So if the binary type right is oh, how do we debug this in a nice way? I'm gonna go through this again. I'm just gonna go to the toilet. I'll be back in 2 seconds. All right. To do any typing of string intending for the identifiers. I don't think I do. Turning. What is interning? I know what interning is. Okay. So what the hell is wrong here? Really, I'm setting it a few places. I'm gonna see exactly where this happens. unresolved types. That's number 4. That's number 5. I think we have one more place. Oops, yeah, one more place. Okay, seems like we have an unresolved type in 1. I'm gonna print the passes here. So while this is true, we're gonna need 2 passes on this, I think, currently. Now let's make it a little bit more verbose. We're doing many passes, what the hell. We probably need to do like 1 pass for this one. So the first pass is just typing everything. It can't type the token because that's not known. The second time it is resolving this link. So here it's resolving that IPv4 is the U32. The second time it's resolving that token is the U32. So now it can type this. I don't know why it's doing a new pass here. It seems to have a few errors on the first thing. Checking if I is inferred. I'm gonna delete that in the tree. So we see what's happening. Okay, let's have them both up at the same time. Thank you for following. The last time it's only 6 and... Okay, so here we have an unknown type, which is weird, because all the types should be resolved. Let's print the type as well. So this is unresolved because it gets the type kind 4, which is weird. It gets the same type here. So why isn't that resolving? I think this is using the same declaration. So I think that might be the reason for one of the passes. I'm gonna print the address of that, of the current pointer being typed. Print it again here. Okay, so we don't type this. This is never a valid type. So this is the only thing which is happening. And a valid type is something which is not unknown and not inferred. This is resolving an unknown type. Well, we're not resolving it anywhere. Okay, this is looking up the declaration type. I think we're missing a lookup here. I think if we have, if this is unknown, oh, it's looking up the name. Right, so it looks up the name. I'm gonna print the name. And we find the name, so this is really weird. Oops. Looking up name token. So it's looking up the token name. Maybe this is not supposed to work. Okay, it's looking up this one. And it gets a mapping here. I guess that is happening. Wait a sec. First, Mary, what's your stream about? This is we're making a compiler, so a new programming language. Intern comments. There is an achievement last stream. So we have 3 streams previously. I can share the link. I think all streams are uploaded there. So it's here. I should probably add it as a link. Like as a command or something. Does it search in upper scope? What if we move token inside function? That's a good point. No, this is going to resolve an unknown type. So basically, this is happening. Resolve unknown type. Yeah, so what's happening is that this is going on the declaration. This is a declaration, right? So it maps variable to token. I know what's wrong now. It basically tries to look up token and it doesn't find, it finds an entry for it, but this isn't resolved. And I think the reason is that we're not iterating over these types. We're just ignoring those. So when we type a scope, yeah. Exactly as I thought. Dang it. So we're going to iterate over the scope types as well. And then we have the question, what are we going to do first? So I think since variables are depending on types, I'm going to iterate over the types first. But this is nice that it actually stops, because that it doesn't have like an infinite loop or something. That's bad. So everything is a declaration. So I'm going to have the declaration here as well. Iterator. Okay, so now we have a declaration, and this is mapping a type name to another type name. So this might be like a structure or just a type def or something. Thank you for following. Welcome to the stream. So I don't know. I don't think we need to make a new function for it. Here we're just gonna resolve. We're gonna say like declaration type, and we're going to resolve this one. So this is basically resolving the token. Yeah, I think this is going to resolve the token. Let's see. So we have 2 passes and typer failed. So we have like fewer of those now. So it seems that it can actually type. It's looking up the IPv4. Let's see here. It is. So the first pass is looking up the IPv4. It's finding the declaration of that one. What is happening first? Yeah, so it's looking up this first. And then it looks up the type token. So that will be this one. And here it will get that this is undefined, because this is pointing to IPv4, which is not defined. It is defined, but we have to make this kind of link between this one and this one, or this one and this one. So really we have to replace IPv4 with U32, and that's going to go in the next pass. So I'm guessing that this is error number 5. What the hell is that number 6? Got type kind. Unresolved types. So it checks if, okay, I'm looking up the token here, and I want to check what the declaration is in any case. Oops. I want to print the kind. Declaration type kind. So it's looking up token and it finds declaration number 1. Type number 1. So that will be, that's a type basic. I don't know why. This shouldn't work. I'm looking up the type token. Oh, I'm looking up the type IPv4. So I'm not typing IPv4, I'm looking it up. So I'm looking up this name here. And that'll be on the, okay, I don't need 2 iterations for this. I don't need that. This is actually typing in the first run, because it knows on the table that IPv4 is supposed to be U32. So that is a declaration or it's a type. So now we're just looking it up. We have to determine if that is already a valid declaration. Unresolved type. This is an unknown type. Alright, so if this is an unknown, okay, IPv4 is an unknown type, so then it's going to look it up. And then it finds U32, so it's going to link it in. So this is correct, and the token kind is kind number 1, which is a base number. So this is correct. Getting some random things here. And then we're getting new pass with error number 5 and 1. So where's number 5? That'll be, that is in the primary expression. So if I'm having like a 5, I'm going to print a name as well. Where is this error coming from? So we have an error on the test and the data, and test and data. This is probably because they're used in the function here as well. So it's going to look up those as well. And this is working. So the second pass, we're only getting an error on data. Only on data here. So in this third pass, everything is... We're only getting 1. So 1 is not supposed to happen. So where is 1? That's this case. So when the right-hand side is not resolved. Thank you for following, by the way. We have to figure out why that happened. Why do we have... Like, this is caused by the right-hand side cannot be typed completely. And this is 1. So it's trying to type both of these. Type expression. Binary right. So the right hand side is not getting typed. I want to know what kind of expression this is. I feel maybe it's the inference between data and tests. Because this is the only thing which is hitting. We're not resolving anything more. I think we're very close. Yeah, it's a typo there, I know. Seems list is iterated in reverse order. So it resolves token in first pass. Yeah, it is. Yeah, as long as you don't have like, if I had another one, with this being U32, oops, and this being AA, it would require one more pass. So then it's having a new pass with typing this IPv4. But then it's doing this together with the inference of that one. But we still get the same error. So this will require a new pass. But since like this is just an unknown, we know this is an unknown, so it's just gonna look up this on the current scope. Or it's gonna look up that symbol. Does it work if you put them in reverse order? That's a nice idea. I'm gonna try that. No, it doesn't work. So what I'm thinking, I think that this doesn't work. The data and test. So I have to look into what's happening there. The right hand side won't get typed. I want to print, before I'm typing this, I'm gonna print typing right hand side, typing left. I'm only interested in the left hand side, in the right hand side, sorry. And then it's going in there. This is gonna print a whole lot of things, but I'm only interested in some of the things here. I think it's the primary. I'm gonna check this one. So this new pass is typing, everything is just returning all the time. And here we have the 1. So we have 2 left-hand sides. Yeah, so that's like recursing in. And we have a 1. So after the left hand side, the right hand side is first typing a binary, then it's typing a primary. Let's just check if this is actually working. If expression type, then do this. Actually, I'm gonna undo what I just did. I don't want to print all that. I'm gonna print in the primary expression if this is not resolved already. I want to check if that's happening. Okay. So that's not the case. We have an expression type. Gonna check the unary as well. No. It's probably the binary expression. It takes like an unresolved binary expression, and how do I know what is going on here? I'm gonna try to print what exactly this is, what kind of node this is. That's better. Gonna print the binary right kind. So this is kind number 3. So binary number 3. 1, 2, 3. That's a multiplication. That's a multiplication. Now the right hand side is a new expression that is a multiplication. Where am I using multiplication here? I'm not using a multiplication unless I'm using this one. I think the error might be there. Then it's typing it. That's interesting. So the problem is when I'm having these pointers. So I'm doing arguments of I, which is being converted to an argument plus y plus I, which is being in a typer converted to an argument plus I times size of arguments. I'm gonna do unresolved binary. Okay. So an unresolved type. That's the yeah, I know what's going on. We're actually handling that here. So the parser, no. Yeah, the parser will make this kind of structure. And then the typer is going to go over, because the parser doesn't necessarily know this argument type. Because in this language you can define like a type. This is a variable, which is a U32, and then you can use the type up here. So when the parser goes down here, it can't really, like if this is a pointer to U32, and you're doing something like typer++, the parser doesn't necessarily know how much this is going to be incremented by, because it has to know what this is pointing to first. So this is just being constructed as argument plus I, and then I go over everything later. And if this is a binary expression, which is plus, and this is a pointer, and this is just something else, I guess. If this is another pointer and this is a pointer, then I'm making this multiplication node here. So that's what's happening, I think. So basically we're failing to type that multiplication. And the multiplication is going to have the same type as the original right-hand side. So when I'm assigning, yeah, here's the error, definitely. Yeah, the hashtag sizes doesn't have a type. That's gonna just, I think that's gonna be like a compiler keyword. Size offset or something. But this is like the size of operator. It's gonna, we can do it like this. It doesn't, this is just what I'm replacing it with. This is just, this isn't really existing. Just swap token. And you pass the correct order, since list is iterated in reverse order. What do you mean by that? I'm iterating the list in the same order that it's added in. Thank you, Science0. Big thumbs up, thank you. X is a U32, Y is equal to X. Yeah, that will be better. So we should declare it that way. That's going to require one pass. But you shouldn't be forced to do that. You can type whatever you want. It's going to make the compile time slower though. Wonder if store nest as a literal pointer tree is actually the right thing to do. How would you store it? Arguments is an operand. Argument is an operand. Yeah, okay. So if I have a binary plus, I'm storing the right and left hand side of the operator. Left hand side, right hand side. I want to make a function for if things are a pointer. I'm going to make it up here. It's a valid type. Bool is pointer. And the question is, should I take in an expression or a type? I think I will take in an expression, because that's what I'm having here. So I'm going to check if an expression I kind of want both. Binary right type. It's not a pointer. I want to check if an expression is a pointer. Return expression type kind is equal to type pointer. So then I should be able to say, like, binary left. So if none are pointers, it should really be combining these types here, but that's fine. I'm just assigning the left-hand side, propagating upwards. that is fine. Here I'm actually resolving a new type. Like I should be resolving it here. Like at this point I know both. So at this point I should be resolving it. So type resolve is equal to true. I probably want to take this at the very end. Like after it has been resolved. Left kind. And then we're checking if both are pointers. So if both are pointers, then you can't use that operator. And then you're checking if the left-hand side is a pointer. If the left-hand side is not a pointer, yeah, if the right-hand side is a pointer and the left-hand side is not a pointer, then you're just swapping those. So we like normalize the expression here. So you can do the same algorithm here, depending on the order, because that doesn't matter. I'm using the type kind down there. I don't think so. So I'm gonna do this. Oops. Unintentional. All right. So this is just swapping those. This is an error here. We're resolving the type. And this might be wrong. I think this is the issue because left doesn't have a type. I think left might have zero. We're setting the expression type equal to binary left type. And binary left typing it here again. Let's see what we're setting this to. Oops. Oh. Why didn't that work? I think that is because we're setting this here. Type resolve is equal to true. Let's delete this one. Typer failed. Is a pointer is a pointer. Yeah, so this won't happen. Ugh, this is so dumb. Expression type. We're actually doing this correct. So the expression has a type there. If it's a binary minus, we don't do anything. This is a little weird. I'm gonna see if there's something with a print. It is still failing. Okay. I'm beginning to think the for loop is the problem. And the for loop has a little like special type thing. So this is not the problem. The for loop is the problem. So I guess I had an unresolved type. if not I get typed. Where's the loop here? Type loop statement. This is typing the initial statement and the condition and the pass statement. And then we type the body here. So the question is, where am I placing those variables? I want to print what I'm inferring. If that is inferred, then I'm gonna print like inferring binary left. Thank you for the follow. So I'm inferring I. And I'm inferring test and I'm inferring data in the right order. If I was to change that, it would be inferring test and inferring data in two different passes. This is a fucking stupid pass, the last path. What is wrong with this? I'm gonna do something smart, because I believe the loop is the problem. So I'm gonna be printing the state here before and after the loop. Before and after the loop. So it has false, false, and then true, false. So the problem is in the loop. And the problem is we have an unresolved type. So the type resolve is false, and we have still an unresolved type. So where is that happening actually? Let's see. Still false. Check the condition. Unresolved type in the condition. Okay, so we know where the problem is now. So I'm going to delete this. This is the problem. We're having true here. Unresolved types. So this print expression doesn't resolve any. This expression. So the loop statement. So the only loop I'm using is this. And we can see how that's being constructed. That might be interesting. So the loop is an init expression here. This is an inferring I is 0. So I have to check that I is 0 here. And then the condition is a less equal between I and argument count minus. So it's failing to typeset this. Starting to think I want. To rewrite my Astor store that knows in dynamic arrays. Yeah, I was told by some other guy that that's a good idea. You only traverse the actual tree once, and then you rebuild linear tables as you go. Like the first pass, you're rebuilding linear tables. So we're just doing one ast pass. But he also said that for optimization purposes, it is preferred to keep those expressions in the tree form. So I didn't really know what he meant by that. But he said that that was a good idea. And I know that guy is knowing what he's talking about. So I think I'm gonna just read the mail once or twice or 3 times. But I think that might be a good idea. How to walk the ast. How do you walk the ast? What do you mean by that? What font am I using? This is called... I can't remember. This is called Source Code Dark Pro. I only have 3 videos on YouTube, unfortunately. So it's failing there. I don't know why it's failing. I'm typing the expression of the loop condition. So basically, I'm typesetting this. And during this, I'm having one unresolved type. So there is something which is unresolved. And I believe that is the identifier I. So if this is a binary expression, but I'm getting error number 1, which is a little bit weird. It's a primary. Like I'm having a comparison, so that's a binary expression. A binary expression between I and a new binary. So the binary fails to typeset this. Or this. I'm gonna take a look at the binary because that might be the problem. Type binary expression. So it's first going to type each leg here, and then it's checking if this is inferred. It is checking if binary kind and binary kind is equal to minus. And if that doesn't work, I'm gonna say like else. Then the expression type is going to be equal to binary left kind, because they should be the same. Like there is some, we have to consider the types here, but I think, oh, binary is not, it's equal to binary. Why can I not use binary there? 166. Incompatible types. This is supposed to be type instead. Okay, there we go. Fuck. Unresolved. Oh. Unresolved is equal to true. Well, this is happening. Is the binary right? Okay. So the problem is a binary expression where the right hand side can't be typed, which is probably here. So it doesn't type this minus. This is really only checking the pointer. So this is gonna happen anyway. I'm gonna assign it to the left-hand side. There we go. But we're getting weird data for some reason. And we're getting the same each time, each single time. Oh, this is uninitialized. Fuck. So this is going to require one more pass, but it's going to have the same value. Okay, nice. Perfect. Okay, this is working. That's great. So now I can actually do type inference. And I don't know how good it is. It's hard to say from the typer how good it is. Like, what it's going to be able to type. And especially the functions is a little bit hard. But if I have like, and here we can say what it's typing. So we can check from this table if it's right. Let's do something a little bit more complicated. Like I have these arguments with a double pointer to char. I want to see what the first char is. So I'm gonna say C is equal to, I don't load chars though. We have to load chars first. I'm not going to specify the type. I'm just going to say this is what's at the argument. And I'm assigning C is equal to that. There's going to be an assignment with C. And it checks C, and that's assigned 1 byte. So it types, okay, this is fucking cool. I'm actually so happy now. This is working. But this is very simple type inference, and it gets much more complicated if you're having templates and stuff like that. But I'm really happy. We have to start one place. Let's make this work first. So I want to see what the first argument is, which is supposed to be a slash. What is this called? Is it called a slash? I think it has a different word. I think it is something else. Let's just print the char. And this might be wrong now. Oh, this is right. I don't know why that's still working. Maybe because this is initialized to 0 something. We have to fix that. Good evening, KF1. Welcome to the stream. I'm writing like a custom language compiler, but I'm gonna make an ARM backend for it because that's really what I want to use it for. Data's not initialized. Yeah. So floating point, no. I'm gonna be doing that later. There is some like, I don't know how floating point work on x86. I think it's you're using the IMM registers, IM registers. I'm gonna rise my desk a little bit. There we go. Oops. All right. So now we can actually start with what we were supposed to do, which is the structures. Yeah, so let's make a structure. We're gonna type that one. I'm gonna make this minimized and let's move this over here. So now I want to be able to type, I'm gonna make a new, let's see first if this is giving an error. It should give an error. Yeah, so declaration is already existing. And that's up here. So now we say variable is equal to token. and we're not doing anything with it. So this should be fine. So then token is just an empty structure. Oh wait. Why am I getting a segfault there? Am I doing something with a variable? So that's working. I can't access the variable. I don't know why. I mean, that is a variable which has size 0. I don't know. I don't know. Anyway, let's make a union and make an anonymous structure. Let's call it just A, B, structure C, and then we're gonna make a tag structure. So I'm gonna just give it the name tag, and this is D. So now so this is, this seems right. So now we have to go over and we have to fix all the offsets. So I'm gonna give each single member, so like A is a member, B is a member, like all named members is gonna have an offset. So like any struct members, it is not gonna have an offset. We might type the offset anyway and just use it to compute the actual offset. But we have to go through the actual structures and figure out what the offsets are. So I'm gonna delete all the numbers first. Looking up type, print. New pass. There we go. Thank you for following. Thank you very much. Welcome to the stream. All right, still working. So now we're gonna actually typeset this structure. So what we get from the parser is something like this. And this might use different types. So I might have like an AA here. So the type is AA. That's a bad type. I'm gonna use IPv4 instead, because that's actually something which has that size as well. So I might not know the type when I'm doing this. So I need to compute. I might not be able to compute all these offsets here right away, because if I don't know the type, I can't typeset this either. Especially with structures, I need to know all the types before I can do something with it. So I'm gonna wait for the entire structure to be typed, and then I can go through and compute all the offsets. Yeah, it's a custom language. Looks a lot like J. It's just like, I don't plan to replicate everything, but I feel like this is a good idea, like with the colon here. But I mean, Google is using the same thing, Go, and it is sort of the standard. And like, I like the way it looks. Something I like, something I don't like. So I'm gonna be using this for something completely different. I think this is more clean. Yeah. Anyway. I really hope it's not going to be the same, because I want to make my own. So that's really not what I'm going towards, what I'm trying to do. resolve a struct type. So resolving a structure type. Okay. So basically I'm gonna fix the type. So I'm returning the actual type. Do I need to return it? I don't think this is gonna need to return anything. This is more like why I'm returning stuff here is it is really only the case where I like have a pointer to something which is unknown. So in case of unknown, I'm actually returning a type which is different from what I was originally having. But I guess I can do the same thing here. The type is going to be the same as type. Yeah. It's going to return type. It's returning it here as well, but that's fine. Resolve struct type. So we need to make sure that the struct is entirely typed, and then we can start computing the offsets. So I'm also going to make a function for computing the offset of this one. Compute struct offsets. I don't know if we're gonna need a typer. We probably need a typer for tracking the current scope, because we're gonna look up the variable in the scope. No, we're not. So we're not gonna need a typer here. That's only when we want to like have a struct member and we want to know what kind of declaration that is. I'm gonna assert that the type kind equal to type structure. And then we're gonna have the struct type is equal to type struct. So we need to go through okay, so how it's structured now. I have from this type here, I can get the top level scope. It wouldn't be nice to have a different list with the things which is unresolved, but I guess it doesn't matter. It doesn't matter. That's like an optimization we can do later. So I'm gonna use the scope table for this. So I'm gonna iterate the scope table because that's faster. And then I'm gonna check that everything is being typed. And if everything is being typed, I can call this function compute struct offsets. All right. In any language ever. C++, do you really think so? Struct auto. Do enums while you're doing structs and unions. We could do that. But then I need to go back to the parser. But we're gonna do that at the same time. We're gonna just do this first. I didn't mean like using the same structure for representing both. Okay, we're gonna go through list node iterator iterates. We're gonna assert that this has, yeah, we're gonna assert that this typer is a structure. We can assert that first. So this is a structure, and the structure has a scope. We're only going to be calling this function if we know it has a scope. So I'm going to be recursing into this one if I know that's a named struct member. And it has a scope, of course. The list will be type, structure, scope is a pointer, and members. And then this is going to give us a struct member. This is a scope node, by the way. We're using two scope nodes. We're using one list node and one scope node. If this is in the scope, I'm gonna be using the scope node here. This is just referring to that specific node here. So I'm either using this for iterating or this one. So now we have a member, and the member is really a mapping between, it's really a declaration. We're gonna check if the member has a type. So I'm gonna call resolve type on the member, which might again call resolve struct type if it is so if that is structure, if that is a structure. Wait a second, member. If this is anonymous, this means that it's a structure. So if that's the case, we're gonna just continue. We're not typing it because this is also contained on the scope as well. And then we're gonna type resolve type of member type, and we kind of need a typer here, so I'm going to give it the typer as well. Yeah, typer. Okay. So I'm resolving that type again, and this is returning a new type. So I'm saying member type is equal to resolve type. So if I was to say like A is equal to IPv4, then I'm replacing that here. So I'm actually going to replace this with a new type, which is the U32. So that's what's happening there. And if that is an anonymous thing, you're going to just continue. So now we need to track when this is being done. So when I know all the types in the structure, I can start calling this offset here, offset function. So when I'm calling, okay, this is resolving a struct type. How do we know where can we store if this is being updated? This is just going to return the same value. Return the type. So really just updating the members. So I can, for example, mark each structure with, like, if it has any resolved, unresolved childs or something. Or the scope can actually contain that information. We have a very little scope here. So we have members. Thank you for following. Welcome. Stian Set. I think that's a Norwegian name. So untyped members. So for each scope, we're gonna assume that this, I'm gonna get the scope first. This is a start scope. Straight scope. Thank you for following. And then we just set the scope untyped members equal to false. We're gonna assume it doesn't have any untyped members. And if this change, so if this is new, if the original type pointer is not equal to this one, is resolving it. Because we can't really then do it there. So I'm gonna save the pointer first. Oops. I'm gonna call it previous. And then we're updating it here. And then I'm gonna say if previous is not equal to member, then we're gonna set the scope untyped members equal to true. And we return the type. So untyped members equals true. So that is returning a type. We also need to check, like, if that is this the best way of doing it? Member type might also be a structure, which might contain a new thing like this. So we might need to propagate this. I don't know. Anonymous straight inheriting. So lambda that does nothing. What is, like, lambda's functions, right? Straight S. Thank you very much for your sheet. Thank you very much. He's watching a stream. Taking a look at GitHub repos. Yeah, that might be true. Like my previous job at Microchip, I don't think they even saw my grades. My grades are not that good because I don't like the subjects. I'm very slow now. We can just check the parent thing. Yeah, so if either this type changes, or so if the type doesn't change, which is a structure, and if I'm not sure this is the best way of doing it though. If this is a structure, what I'm returning here, if that's a structure, and that structure is anonymous. If that has a scope, then I'm gonna say if that scope is being set by something, if that scope has n-time members, then the current scope n-time members is equal to true. This is just propagating the Boolean value, and then I'm returning the type. I'm not sure this is the best way of doing it though. I can be commenting here a little bit. If the returned type is a tagged structure, if the return type is a tag structure and contains typed variables, we propagate that. I don't know how to write it. I'm gonna fix it later. Let's focus if this is working. So I'm resolving a type, and here I'm resolving a top level type. So I'm gonna check it here instead. So I'm gonna say if declaration type kind is equal to type structure and declaration type structure scope n-time members is equal to false, is done. Then we're just going to say struct typing is done. And if this is a struct type, we should probably just check if it's already done. So if it has a scope and if the scope n-time members is equal to false, return. So if it's already false, I'm gonna just return. And then I'm typing this again. Okay, let's see. Resolve type 408. I need to make this forward declared. There we go. We have segfault. Resolve this. So it's typing the structure. And it's returning. Scope untimed members. And I'm recursing down here. I wonder if I'm using something I'm not allowed to do here. Member should be a valid pointer. So this should be valid. Maybe a member doesn't have a type. Yeah, it should. It might not have a name. I'm wondering where it fails. Oh, it fails before that. It fails here. It doesn't have a it seems like the scope is wrong. The scope seems right. We're returning nothing here. If this hasn't, then we're gonna return the type. Fuck. There we go. So it's typing the structure. That doesn't really tell us anything. I'm gonna check if this is actually typed. Then we're gonna print this. Else we're gonna print like a line. This means that some struct member isn't typed. Which is not happening. That's fine. So let's make a program which should fail there a little bit. So I'm gonna set IPv4 to the value AA, which is a U32. So I think that also might work. Yeah, that might also work. Let's see here. I'm using IPv4. For struct A is supposed to be IPv4. So struct member A is IPv4. It's done with the typing and it still has an unknown type. Thank you for following. Propagate, yeah, it's a typo there. Thank you, Tom Rocks. Yeah, it's really fun. The at operator, it's basically the deref. So we're looking at the address, you're looking at the value at this address. That's why I'm using the at operator. I think that's really nice. I haven't seen it before. I was told that one other languages are using it as well. Language look almost identical to John Blows J. It is not gonna look identical when I'm done. But this is looking very close to many languages. But it's different. It is not supposed to look like it. So we have, even though we have an unknown member, it still tells us that it's done. Struct typing is done. So if I'm having an unknown, I'm resolving unknown type. And I don't assert declaration type if it's valid type. Type resolved. So if this is not resolved, it is just returning the type. So it doesn't really make sense to just do this. We have to test a little bit more. If that is different, I would want to know like if I'm resolving anything here. Because if I'm resolving an unknown type, it's basically the same. So I don't know. I can have a global variable for a structure, which is telling if I'm entering a new structure, I can store it somewhere. I can store the current structure. I can store I think that might be the best thing we can do. Because this is kind of not working. Like this is correct. It is setting untime member, like this is equal. So this won't get set. While there still are untime members. So I want to detect when I'm doing this. Typer unresolved types. So I'm gonna just have a global variable in the typer. I think that might be the best ID currently, just to make this work. So I'm going to save the current structure. And when I'm resolving that structure, I probably need to check it. Is that a structure? I'm setting typer current structure to declaration struct, which is a pointer. Which means that resolve type knows if this current structure is something non-zero, we have a current structure. And then we can make this much simpler. Yeah, okay. What we can do, that's actually kind of better. Wait a second here. I don't know if this is gonna be good. To be honest, I don't know if this should be done ever. What we can do, because we're already setting one variable, so we can actually save the state. We can save if there are still unresolved types. So I have two Boolean values for doing that. So I'm gonna do like saved unresolved is equal to typer unresolved types. So I'm basically saving this state here, and then I'm setting the typer unresolved types to false, and then I'm resolving this type. And if this is a structure, if this is a structure, I'm not going to check the untimed members. I'm just going to do like if this is a structure. Now we can check the unresolved types. So if unresolved types, if I still have that, and if the declaration type kind is equal to type structure, so if I both have unresolved types and it's equal to structure, I have to mark that as unresolved or something. And at the very end, I'm gonna do typer unresolved is equal to either it's going to be typer unresolved or saved. That was really smart. I'm actually very happy with that. I'm just saving the state and I'm setting it to 0, and then I can detect if I'm resolving any new types between these stages here. I could probably just do it if I'm having a struct type, but I'm doing it anyway. That might be, we can probably fix that later. So if it's unresolved and it's a structure, I'm gonna say declaration type structure scope false. Actually, we're gonna do this inside here instead. How's the logic gonna be for this? I'm very slow now. It's probably the colors. Yeah, this is day number 4, I think. Tells all the feature but doesn't force me to use any of them. Yeah, I agree. Okay. Like we have to check if this is a structure first. No, I'm saving it anyway. So for each single type, I can know if a type is still unresolved. So if a type is still unresolved, I don't care if this is happening on normal types, but structures are much bigger. So I want to avoid resolving a type if it's already happened, if it's already done. So I'm gonna say like top if declaration type, if it is a structure, this is so dumb. If this is not equal to structure, or so this is happening if it's equal to structure. I can just say untimed members here. So if the kind is not equal to structure, or the structure has untyped members, it's going to try to type this. So it's going to be a little bit speed up. And that's going to set the unresolved types to false. So I'm really going to set it to false inside here. No, I'm going to set it outside here. And then I can move everything here inside. That's better. So now this is only going to happen if I have some kind of unresolved type. I'm going to restore this afterwards. Okay. So if the structure is not resolved and I have a structure, then I'm gonna set this to whatever the typer unresolved is. So once that's becoming true, then I'm gonna not do this anymore on the structures. Okay, we're getting there. This took way longer time than I actually should have been spending on this. If this is a type struct and the declaration type struct scope and now untyped members, now we're just going to say if this is a type struct. Okay. Then untyped members is equal to typer unresolved types. I hope this is going to work. Anonymous. I'm setting it to false in the beginning. Untyped members. Wait, we have to initialize the structure with this being set. So when I'm starting, so I should instead be calling this type incomplete, because then it's zero initialized. And then I'm setting to not unresolved types. And then we're doing not this. And then this is being set back again. I'm gonna check if this is a struct type. This might be redundant. Typing structure. Typing structure and done. So you type in the structure, typing, and then it does done. Just doesn't know why. We're still getting IPv4. If things has been resolved during this, if it still has unresolved types. So once this is done, I don't need the typing complete. I'm just gonna resolve the member. Member type is resolved type. I'm gonna check if this is unresolved. Is done. Gonna check if it's done. I'm probably using the same. Okay, is done. It is done here. So this means that everything so the unresolved type is equal to false. So between this point, like it's resolving the types here, and nothing has been resolved. Resolving type. Resolve unknown type. This is being set to true. I'm gonna track that. That's not happening. Let's take a look at the members. So strict member A is an unknown IPv4. So if it's anonymous, I'm gonna continue here. Let's print the member. So it's not typing any members. So that explains why it doesn't work. If declaration type is not equal to the typing structure, hello RedTube, Red Tuft X. Welcome to the stream. I'm gonna comment a little bit more, so it's easier to come back to it. So it's typing the structure, and this is equal to false. So this will be happening. So typing structure, typing, and is done. So it types this structure here, and it resolves the struct type, And if typing complete is equal to true, fuck. Typing complete, I'm not gonna set the typing complete there because I'm not setting it elsewhere. Okay, now it's supposed to work. There we go. Name is an unsigned 4, and we're doing how many passes? I don't know, probably just 1. Dang, finally. Okay, this is ugly. So this is just for the printing. We are using 1 we save. Still untyped. Okay. Declaration type. Typing complete. Okay, a little bit like, I'm not a very fan of this implementation, but it's gonna work. So let's try something a little bit more complicated and see if it still works. I'm gonna say like XX is a U32, and this is gonna have the type of XX. Then it's gonna have 2 passes. It still finds it, which is good, but now it's gonna require like multiple passes. I don't really care about how many passes it does. Yeah. Okay, let's continue. Let's actually find the offsets here, which is the next step. Where am I printing stuff? I'm printing typing member. I'm printing error somewhere. There we go. Perfect. Test equal to 4. Thank you for following. I don't know what's happening there. Is it changing this or something? All right, doesn't matter. Oh, finally. Take some more coffee first. What is everyone's opinion on Go? I haven't tried it. I've seen some of the syntax there, but I haven't tried it. Non-starter. Everyone is hating on garbage collection, and I don't know what it even is. I think I know what it is, but I don't know. Not knowing what garbage collection is makes me feel so stupid. Okay. So now we're gonna actually compute these offsets there, and everything should be typed. Let's okay, everything should be typed. So now we need to call this function compute struct offsets with the struct type if everything is computed. So it has to go through and type it once. So this will happen at least once. And if that is structure, we can check if it's already typed. Thank you for following. Is unresolved types is equal to false? I'm gonna say instead if typing is complete, you compute the struct offset with this type here. All right, that's better. That's much better. You're on the right track. Don't bother with unnecessary knowledge. Okay, that's good to know. I guess the garbage collection is not that important after all. Compute struct offsets. Yes. So we need to keep in mind. We need to keep in mind where those are. So if we have some kind of unnamed, like this will get the offset. If I had something like a U32 here, then this will get the offset U32. Because this is an anonymous structure and this is an anonymous structure. So when computing these offsets, we're not really gonna be using the scope at all, because the scope doesn't replicate the structure. We need to know this kind of structure here. So this is also a member, and each member has an offset. So we can actually use that member. So I think we're gonna, yeah, this is gonna be inside this one. So we need to check if the previous, yeah. So I'm gonna, okay. So this is gonna compute some kind of offset. And I'm gonna do that. Like this is gonna have an offset. For example, 4. So that's fine. Okay, I'm not gonna track that. And then for each member in here, I'm gonna check if this is if this structure is an anonymous structure, then I have to add this offset here with a new offset there. And if this is not an anonymous structure, I'm just going to compute the new offsets. So let me make an example to make that clear. This will have, that's boring. Let's do this one instead. Offset here will be 4 plus 4, since this is an anonymous structure. If this was a tagged structure, then it doesn't matter what this offset is, because we have to go through this member, and that's going to add it manually in the generator. So then it will just be like this. So this means we can compute this by just looking one step back, or just looking at the struct I'm computing here. So I think that's going to be doable. This is computing the struct offset here. And this is do we know if this is, yeah, this has a scope. So I'm going to be using the scope variable to determine if this is an anonymous structure or just a tagged structure. Okay, so we need to iterate through all the elements. We're going to handle both unions and structures here. So list node iterator. struct members. I'm also gonna propagate an offset here, I think. I'm gonna be, do we need to do that? If I set the offset first, it is going to be fine. Let's just try something. Struct member. This is a list and not the scope node. So for each member, it depends if this is a union or some kind of different thing. So usually I can just give a base offset here, I think. Let's make an offset variable is equal to 0. Normally this will be 0. But what I can do, I can just say if this is equal, if type, no, if structure has a scope, I'm gonna do something better, like more visible for this, because this doesn't really tell us anything. But if it has a scope, it's basically, it has a name. So if this has a scope, the offset is gonna be 0, because we're gonna start indexing from 0. Otherwise, this is gonna have the structure offset as the starting point. So this will only track what it's currently in, and this will be what we're gonna start with. And we're gonna have an alignment as well. Which is 0. I'm gonna assume 0. Yeah, what is the alignment? I'm gonna propagate the alignment as well. The alignment doesn't really matter. Yeah, we're gonna just have it like that. So we have to first check if this is another structure. So if member type kind is equal to structure, we're gonna recurse. Compute struct offset from this member type. So that's gonna recurse. So at the very end of this, we should be able to, like this should store the size of this type here. So we should have a size here. And then we might do something different based on if this is a structure or a union. So I'm just gonna check if it's a structure or union. If member type kind, we're doing this all over again. No, if no, I'm off the track now. If structure, that's what we're having. If struct type, don't we have a struct type? Yeah, also if struct is a structure, union. So you're computing these things a little bit differently based on if it's a structure or a union. So in case this is a structure, we're gonna assign the offset first, and then we increment the offset. So the data will be the first element. We're gonna just assign the offset of this one. So member offset is equal to offset. And then you increase the offset with the size of the member, which should be computed based on this entry here. So this will compute the size of the substructure. Thank you for following. Okay. So that's the offset, and we're gonna increment the offset with a size. Does the member has a size? I think the member has a size. I don't know why the autocomplete doesn't work here. Probably because of the plus equal. And then we're gonna align the offset with, we're gonna align the offset first. We're gonna align the offset. So I have to use the align function. I think I'm using some alignment in the generator. Align. That's static, so I can just use the same variable here. The same thing here. I'm gonna fix that later. This is aligning a number with some kind of alignment. I'm gonna align it first. Offset is equal to align offset with the member size. So then this will have a correct offset. And yeah. And then we're setting the member offset equal offset, and we increase the offset by the member size. And then we need to track the alignment here. So alignment is 0, and this will be bigger. So this will actually, like if this is again a structure, this will compute a new alignment. This will be like size and alignment. This will like propagate upwards. If alignment is bigger, is smaller, I'm gonna see the new alignment is bigger than alignment. Alignments. Then we update the alignment. So that's in case of a structure. And let's see what it is for union. So the offset is really going to be just 0. Every single member at the union should be 0. So member offset is equal to 0. And we need to check the size. We need to contain the size here as well. And this member offset is 0, and we're going to do the same thing with alignment. We can just do it down here. That's happening regardless. Yeah, I think that's gonna work. So we have to figure out what the size is. So here we have to say like, let's make a new variable called size. Size is equal to 0. Yeah, which should start with 0. And then we're gonna say if member size is bigger than size, because this is a union, so it should only contain the biggest member. Then we set size equal member size. And in case of this, offset is align member size. So we should really increase the size with size plus equal offset. So this will be the size of the member aligned. So at the very end here, we should have got size something. And alignment and offsets. Member size. Member doesn't have a size. But member has a type which has a size. If member size alignment computing, this is not allowed. So we have a floating point exception. The reason we have the floating point exception is because I'm aligning something here. And this basically divides, I think, modulo 0. I think the alignment is 0. So I have some kind of alignment of 0. Alignment is 0. That's not supposed to happen. If member alignment is bigger than alignment is equal to this. Thank you for following. So member alignment is 0. It seems like all the member alignments are 0. Thank you for following. I'm iterating over all these members. Let's actually print the member first. So member T, member A. Member nothing? Okay, so the member nothing is an anonymous structure in which the size is 0, I believe. Let's print the member size as well. Oh, I'm using member type alignment. Fuck. I was wondering why that was still 0. So now it's computing. Member alignment is 4. Member T. So what is T? T is a union. So in order to compute the union, is that as the first recurse down? Okay. Let's just check it again. is equal to the member type. And then we're using the member type instead. I think that's cleaner. So the member type should never be 0. Or the alignment should never be 0. It should be 1 or bigger. And that is because I'm not updating this stupid thing. I should be updating it at the very end. So basically I'm getting unions and they're not getting updated. So the size and alignment is still 0. So I need to update it here. Struct alignment and offsets. That's a struct type. So I need to actually go and fix the size as well. So alignment. I don't know exactly what I need here. This is the offsets. Then I need to get the actual type. So I need to set the type alignment. And the size is equal to size. So I don't need this part. So the struct doesn't need to know the alignment. That's contained inside a type. And that makes sense. Yeah. The only thing the structure needs to know is the offset. But I'm just going to contain it like this. The struct alignment. Struct member. And a structure type. Like the structure type shouldn't have this. The member should be having that. Having like a list of struct members. Member type, that's fine. And then we recurse down here. So void, offset is equal to line, increase the offset. You set the member offset to 0, because that's a member variable. Struct offset. That is really the struct. The struct should have a size and alignment, and the member should have an offset. That is correct. I'm just doodling around with this start case. The start structure is also. I'm just adding a unique member. Yeah, okay, yeah. So each, that makes sense. That makes very sense. So each member offset is going to be updated with the offset. Oh, you're actually doing that inside there. So the offset is fine. The member offset is 0. So I'm actually assigning the member offset. That's working. And then after this is returning, I'm setting the alignment and the size. Struct offset. Struct offset doesn't work. I kind of need to have like if the struct is itself a member. It can be done very simple, but then I have to recurse in all the time. Oh, I have to, I'm sorry, I'm in my own world. I'm gonna check chat more often. So the offset of the first member will be its size. So it should be, okay, so what I'm doing here, let's make some more space. I need to compute for each single member, like what do we really need to know? So if I'm doing something like token, and this is like, I'm gonna call it un for union. I'm gonna call it u for union. Token u, and let's see, I'm using structure number a. So then I'm actually gonna, in the graph, when I'm actually parsing this, that's gonna look like this, I believe, because I'm gonna parse it that way. So I'm gonna parse this one, I'm gonna give that the pointer of that one to the next, this is like a suffix expression parser. So in the graph is gonna look like this. So what I'm doing, I'm recursing down here first. This is when I want to find something. So the last thing here will be a primary expression. This is like a primary expression, and this has an address. So this is fine. This has an address, which has a size and alignment. Yeah. So this alignment only like comes into place when I'm allocating this on the stack or globally. That's when I'm using the alignment. The size is also just for like knowing how much space I'm gonna set aside for this token. So both the size of an alignment for this one is only used for setting the address. And in order to know the size of the alignment of this one, you have to know the size of the alignment of all the members. It doesn't matter if that member is a structure, a union, it doesn't matter. You're just gonna go through all the members and you're gonna find the member with the highest alignment, and that's gonna be the structure alignment. And if it's a structure, it's gonna find the sum of all the sizes, and that's gonna be the total size. So what I have to do with the size and alignment is just to allocate the base structure, like getting an address of that one. The rest is just offsets. So when I'm then recursing down, in the generator, I'm gonna eventually come to the token and I'm gonna get an address, and then I'm gonna look up this u inside this token, and that is supposed to give me an offset, which I'm gonna add to this address. So here I'm gonna add 4. And then I'm recursing out again and having a. So what offset does a have from this u? Not from this structure, but from the u. So a has offset 0. This will be address plus 4 plus 0. So I'm just trying to, it's very simple. I'm just trying to assign these offsets in a nice manner. That's what I'm doing. Correct 0, not the size of a. What? Can your memory allocation use negative margins though? What do you mean? Okay. So the thing is that when I'm going to compute the offset from this A relative to this U, I need to store, like if the member is a structure, I need to store the member offset in the actual structure because I'm getting the structure here. So if the structure has an offset here, I will need the offset there. And yeah, so member kind. So after everything, I'm gonna check if the member type is equal to type structure. If this is a type structure, I'm gonna say member type structure offset is equal to offsets. And I'm kind of changing it here. But that's fine, I'm gonna just set it to member offsets. So like all this fuzz is because I'm gonna support anonymous structures. That's why I have to propagate this stupid offset. Web joke. I don't know any web development, so I didn't get it. Yeah, so here I'm propagating that one. So basically the offset I'm computing for this member will be the offset for this one. So it's inferring something. I want to print when I'm entering this function, when I'm entering this entire thing. Okay. So you're getting size 4. Let's verify here. We're getting size number 4. Offset is 8. I'm printing offset where? Okay, so offset is 8. That's because the first size is 8. I'm not going to print it there. Got size 4. Got alignment 4. Got size 0. So basically, it recurses in here, and it fails to update the size. This isn't supposed to return anything. Yeah, so size is still the size. So the thing is that I'm recursing in, and this doesn't really update the member type size. So if I was to print member type size here, it will be the same. Member type so this is correct, this should be 0, but it shouldn't be 0 after this point. Here's something wrong. I'm using something member type size. Also, wait a minute here. This is inferring stuff. If I'm not using, this is failing because the first pass we don't know all the types. So the type will be 0. That's correct. That's the problem, I think. If I'm giving this U32 instead, same member type size is 0. It's going in here. If the member type kind is equal to, oh, it does this. Yeah, it does do this. The problem is that this is 0. So generating member data. Okay, so this is working. It's first generating member data, then it's generating the struct member U. And then it has to go in here, recursing in, and it's going to go through all the struct members of U, which is 3. It's going to start with this one, and it's an anonymous structure. So it's generating a member. The member size is 0. It's the final case which is not working, which is weird because I'm getting the size and alignment is 4. I'm returning somewhere. Am I returning somewhere? This is local variables. For each member, I'm computing struct offsets. So this will call itself with a new member. It will do all this. And it will set the size here. So it will print got size and alignment. So this will actually be not for the first one, but for I want to check if this is a union or not, because this is a union. It's not that far away from the right solution, I guess. Member type size after that's never supposed to be. That's 4. I'm going to print the actual member of this, so I know exactly what's happening. So member size after an anonymous structure is whatever. It doesn't have a name. Let's try to name all the structures here. Just to see if it's right. So we're generating a member II. This doesn't recurse. And generating member III. It first takes this one and then it takes this one. Oh, it actually recurses to III. And then it generates the member C. And for the member C, it gets size 0. So there is one size which is 0. So the structure should have a size here. Assert. It should have a type, and the type should have a size which is non-zero, and also an alignment. But that we can check that later. Okay, so generating member. So now all members are named. So the III member doesn't have a size. Which is a struct of just one U32. If member type size I'm only having structures. So size is 0 plus equal offsets. That's the offset. Okay, wait a second here. Plus member type size. Fuck, this is so annoying. It's really annoying. Maybe I've been working for like too long. First parameter to line is the thing. I don't know. I don't know. It is such a simple thing. And I wait for everything to be typed. So I know the type of every single thing. I'm computing the struct offset from the declaration type. Because I know the typing is complete. I'm asserting that this is the type struct, that's fine. I'm saying that the offset is going to start, if it has a scope, it's going to start at 0. Otherwise, it's just going to go at the offset. And alignment is 0, size is 0. I'm iterating over all the members. If the member is a structure or a union, doesn't matter, then it's calling itself with a member type, because this is structure, this has a struct type, and the same typer. It's calling itself. So it's calling itself here and it's calling itself there. So here it should be getting like U64, U64. That's got size 8 and alignment 8. That's wrong though. The size is not 8 here. I think I'm mining all the things, yeah. And then I check if structure is a structure. If it's a struct, you're gonna align 0 with, you're aligning 0 with member type size. Can we align 0? Because the offset is 0 at first. serial model or something, that should work. The member type size. And that should work always. Is that the assertion here? Okay. So by not having member type size here, but because this is wrong, we're doing something wrong down here because it's recursing. So for each single member, you align the offsets, you increase the size with the offset. This is wrong. That is wrong. Yeah, that's wrong. This is supposed to be member type size, and then you align the size with the offset afterwards. Size is able to align size with the proper alignments. We don't need to do that. We can do that after. We're just going to increase the size here. So increase the size with a member type size. We set the offset. And then we do offset plus equal member type size. Because we align it first. This is correct. In case of the union, every offset is going to be 0. If the member type size is bigger than blah blah blah, we're setting it. We're updating the size. And then we check the alignment. And then if we have some kind of offsets for this member and that member happens to be a structure, we're propagating the offsets because we have anonymous members. Anonymous. So now we should be getting a correct size here. So the alignment will be alignments, and the type size will be align size with the alignments. There we go. Stupid little shit. Okay. That was the issue. Just the assignment there. Not printing anything. Yeah, you can see we're aligning all these things. So I want to go into the tree printer and just, if it has some kind of offset, I want to print the offset and I want to print the size and the alignment for every single structure. So we're gonna go in tree printer on the structure, and we have a structure which is maybe anonymous. We can select size and give it a size, and align, give it an alignment. This is a type. Okay, and the struct member will have an offset. Member offsets. So let's see if this is working. So now we're typing everything with the size and the offsets. It's hard to know if this is right. What's up, said who? We're making a compiler, so we're trying to get the offsets of the structure to work. This it crashes. The problem why it crashed was because I was doing modulo with the alignment of 0. So I should probably make an assertion on the alignments. I'm gonna do that later. So the data, has offset number 0. Let's verify this. And it has size 4 bytes. This is correct. U, which is the union, has a struct size of 16, which is something here. That's correct because this is the biggest size. An alignment of 8. That's correct. And every struct member has the offset 0. Okay. So let's don't type this. Let's have a struct member up here, which is a pointer to a U32. It still works, but now this union is going to get bigger. So the union has size 16. Oh, that's right. 4 times 3. That's let's do like U64. So now this is bigger, and this member is at 0. And now this B member will have a different. This B member will have an offset relative to this structure. Let's do this. So every single union member will have a relative offset through to this base, which means that nu is going to have offsets. So each still have the wrong offset. And that's because I'm assuming everything starts at 0. Struct member 24. This is an anonymous structure. So basically this will have an offset. This anonymous member will have an offset. And we're not tracking that. So if it has a scope, it is 0. Okay, so the offset is always 0. So I'm failing to propagate this information. If this is true, that should be updated. So it has anonymous there. So that's an anonymous thing. I'm going to print the offset as well. So the offset is 0 all the time, which means that this struct member has alignment 24. Which means that the biggest size here is 24. Why is it 24? It's because this struct member here is anonymous. The alignment is set wrong, first of all. Yeah, so since this is an anonymous structure, right? This is an anonymous structure at offset 24, which means that each single member here should be increasing this offset by 24. The question is, do we know this information before we recurse? Or maybe I'm messing up the order now. Like, I don't know the size of the... Okay, I don't know the size of that one. To get the offset of the union, I need to know... Okay, so this kind of doesn't work. So we could just go over all the elements in the union afterwards, after it's computed. Because I know this size here after everything. So here I know the size. I don't need to propagate it further. Okay. I don't know. It is very simple to implement. If I want token new, I want this element here. It's very simple. I just go over each element in this top structure. If I have an anonymous structure, I'm going to recurse into this one. And I'm going to increase the offset when recursing. And then, like, while I'm recursing, I'm just increasing the offset. But then I have to, like, go in all elements and then go back again. I just tried to find if it's a better way of doing that. Because I have to know the size of this one. But then I'm figuring it out in the wrong order. I don't think it's a better way of doing this. Because I have to, yeah, I think I just have to do it like this. And I think it's actually smarter to just go over this after I'm done here. Update. Because this is happening like once. I may be using this structure like 100 times. It's much faster to just do it once. This won't take that much time anyway. So I think I'm overcomplicating this. For the offset, the struct doesn't need to know the offset. So this doesn't need to know the offset. So that's getting simpler. Struct offsets. Member. Yeah, we don't need to do this. Offset is equal to a line. We kind of need the offset. Token new. Alright, so it works. So the only thing we need to do here, we need to recurse through all the members again, once we know this alignment here. No, once we know this offset. Compute the struct offset. We kind of have to do it after. So we're only computing relative offsets here. And then we go through everything again. Make a new function for this crap. And we increase it just to make it faster. Fix struct offsets. So I'm not going to use a typer because I don't need it. Thank you for following. I'm sorry that this is taking so long time. Just try to make it nice, and I can't really do it. So we're gonna fix the offsets after everything, because then we know all these things. So this should be very simple to implement. I'm gonna do almost the same. Let's copy everything. Oops, not everything. And we delete all this and this. Thank you for following. So basically it's going to fix this direct offset. So I'm going to give the initial offset of 0. I'm going to probably make a different, like do a different algorithm later. But I'm going to give it the offset of 0. So this has to go through each member, and it's going to add this offset here. So for each member, it's going to say member offsets plus equal offsets. So for the first time, that's going to be 0. And if this is an anonymous member, we fix the offset first, and then if the member type kind is equal to type structure and it's anonymous, yeah, so if it's a structure we need to recurse anyway. Then we're gonna fix the struct offsets of this member type. And we're going to give it the member offsets, which are probably, yeah, member offsets. So you need to give it some initial thing here. And we need to check if this is, let's just check if this is an anonymous structure. So if the type this should be a struct type. If type, oops. If struct scope, then it means it has some kind of name. Then we're going to set the offset to 0. Because we're going to compute the offset from there again. So I think that will work. Perf. Compute struct offset typer. So now we're getting struct size, struct members 24, 24, 24. And here we have a new member. So this will start typing the members again. Okay, so I think this will work. We have a member A and B. I'm gonna print the offsets so it's easier to see. Maybe this is a little bit small. I don't know. Okay, so the A and B member both has offset 24 and 32. And this is because these members access the offset from the top level. So this can actually be found from the top level. I think this will work. So now we just have to implement the dot expressions and generate the assembly code. That should be trivial. Fuck. Never mind, I'm wrong. Yeah. I'm very sorry, I'm gonna check the chat more often. But I'm in my own world when I'm programming. Okay. So there is probably a better way, but we're basically supporting all kinds of structures now. Union, anonymous, everything. It's not really that much. It is just I have been streaming for so long and my brain is empty. So into the parser. We're gonna go into the parser. We're gonna make a new node, which is an expression. So this is a call expression. We're gonna make a dot expression. So this dot expression is gonna store the token of the dot, and it's gonna hold the expression. Yeah. All right, so now I'm gonna make something which can parse. So the structure are being parsed. So now we're just gonna make sure that we can parse something like data.task.pass.a. Yeah. So we're gonna add the expression dot. All right. So now we have a new expression there. Now we're going to go into the parser and determine where we're going to make that. This is supposed to happen after an identifier. So we should go up to parse primary expression. No. This is a suffix expression. So this is a dot. If this is a dot, we are gonna construct this kind of expression. Thank you for following, Crimson. So you're gonna make a new expression with the type dots. And we have to save the current token, which is supposed to be dots. So the dot token is gonna be copy token. And the dot expression is gonna be, are we skipping that token? We're consuming this token. So basically, the token is pointing to the dot, but the actual lexer is pointing to the thing after the dot. So I'm gonna recursively call parse expression here. Parse. No, this can't really be parse expression. Dot parse expression. So what we're gonna allow, if I have like an array, that might also be a structure. So this is really gonna parse a unary expression up here, because we might have open parentheses, multiplication, deref. What the fuck? No. We're gonna parse a primary expression. That's gonna parse a unary after. So we need to know a primary expression after this one. Parse primary expression. That's the dot expression. And returning dots. Not any suffix expression. And then we need to make sure we can actually print this. print scope, print expression. If this is a dot expression, this is a unary kind of expression. So we don't expect multiple statements after this one. It is just going to be one long arm like this, extending outwards. It is not going to have like two notes after each other. So I'm not going to paint any indentation here. I'm just going to indent print dots. Yeah, just print a dot here. Dot expression. Oops. Return dots. So this is supposed to be an expression instead. Yeah. So now we should be able to write token is type of token, and I want to printf token value, which is token dot let's do just a token a. And we have an exception here, typer exceptional panel. Okay, so it's being printed, I think. Yeah. So we're calling print with the argument, which is a dot expression, identifier a. So we still need to know what the original expression is. So this is just tracking the expression, the dot expression. We need to keep track of the previous as well. This is parsing suffix expression. Yeah, actually I'm going to be calling this one instead. Yeah, suffix. And then the previous one is the dot. So the expression is recursively calling that, and then it's returning dots at the very end. So let's see. Thank you for following. So I'm tracking this. I have to track the name after the dot. So if this is a dot, I'm gonna first say the dot expression. And then I have a name. Yeah, I'm gonna have a name here. Thank you for following. That's very nice of you. So the dot is gonna have a name as well. It's gonna ask for a member. Consume token Lexer. And then we're going to skip the member. So dot, this is going to be copy token and skip token. So it will force it to be an identifier. And that's because a struct member is always an identifier. So copy token, and the member is also a token. Yeah, so I'm gonna make the member a token. A member name. I don't need the member name. I'm just gonna have the member. So now member is copy token, which is supposed to be an identifier, and then you skip that as well. So what you have after this is either nothing, or you have like an array, or and this is also calling it recursively. And then you're returning the dot at the very end. So this will first, it will be called like this. And it will save this one, and it will, the expression is going to be the next part. Yeah, that seems about right. Oops. I need to have this first. I actually think I need to do this, because they're the wrong order. So the dot expression is the previous. Since the dot expression is the previous, that makes sense. Yeah, that makes sense. Token.a.data.test. So I want to print a member here as well. So I want to print a member, and that is a member of this thing here. So dot, and the member, that is the dot member name size. All right, so now we're, what the fuck? Dot member. That is the wrong one. That's interesting. We're copying the token, which is supposed to be the dot. We should be skipping the token first. Skip the identifier. This is gonna skip the identifier. No. We want to do dot member is equal to copy token from the current token. Oof. And then we need to just skip it afterwards. It was getting the wrong thing. Okay, so I'm gonna remove the name member. So this is how we want it. We basically want to access the member test in something which is this. So eventually, we're going to be asking for the member A in the token. So we're going to recurse until we're hitting like a primary expression. And yeah, we're going to be recursing until we're hitting this primary expression. And that's going to give me the structure. And then I can look at this name in this type. That's going to give me an offset. I have to add that offset to the address. And by accessing this member, that's going to give me a new type. And then I'm looking at data in that new type. That's going to give me a new offset because the offsets are correct. And then I'm just adding. So we should be very close now. All right. Okay, so the typer has to do something. The typer is failing. Because we're typing every single expression. We have to handle dot expression in the typer. And they should be simple to handle. Compute compound statement, type expression. So here we're gonna add a dot expression. Thank you for following. Welcome. I'm glad you're here. So type dot expression with a typer. Thank you for following. Welcome, welcome. Yeah, so this is supposed to return nothing. This is just gonna type it. And this is supposed to be simple because we only have one single member. Thank you guys. Welcome to the stream, everybody. Yeah, so let's access the dot member. So that's a dot. And then we have the expression here. So we need to type that one. Also, the dot is an expression, so we need to assign a type from that expression. Which basically means we have to look up the type. Look up in the type. I'm gonna be returning a struct member. Oops. Look up member in structure. So I'm going to be needing a structure here. A struct type. No, I'm just going to give it a type. And I'm going to assert that the type kind is the type structure. And I'm going to assert that's the only thing we actually need. Yeah, I'm going to assert that this is a structure. And I'm also going to assert that this has some kind of scope. Because you can't really look up in an anonymous structure. It doesn't work that way. I'm gonna assert that that's true. So if this is true, I'm gonna basically be finding it in this scope. Thank you for following. and list iterate, type, scope, and members. This will only list typed members. So basically I'm going to assert this as a type. Strict member, and member is list to structure, this iterator, member, this is the scope node, remember. I'm going to assert that the member is equal to false. I don't know if we're actually using this anywhere. Is anonymous is false. We're not really listing anonymous members. I had to include string. If string compare the member name with the name, I'm going to take in the name here. So I'm basically looking up this name in that structure. So if this matches, I'm gonna be returning that member. So now I'm typing this dot expression. I'm gonna first make sure the sub expression is being typed, because we have an inference there. So this is first gonna type expression, which is the dot expression. This is what it's pointing to. And this is going to happen if that is not typed yet. So if dot expression type is equal to 0, then we have to try to type it again. Yeah. So now at this point, and typing expression, that's going to also update those global variables. So I'm not going to change that here. What I have to change, I have to update this expression if I can. So if dot expression, if the dot expression has a type, this is the structure type. And now I want to look up the member in that structure. So I'm going to say lookup member in struct. The name I'm going to look up is the address of dot member name, and the type is going to be dot expression type. Make sense? We're trying to get the member, this member in the expression structure. I'm going to rename this a little bit because it's a little bit confusing. So if we have a member, return 0. If we have a member, yeah, so we have to consider the end case. If we have a member, like if member is 0, we're gonna error token. Thank you for following. I'm gonna give an error on the member, which is a token. invalid struct member. So here we have some kind of member, and that member has an offset, which is cool. So I think we're gonna actually type it here. Yeah, we're gonna assign the offset here. So member, we know the offset from the base address. So I have an expression there. Well, we know the offsets. I don't know where I'm gonna use this offset here. Let's fix the type first. So the expression type is equal to the member type. And then we're gonna say typer type resolved is equal to true, because we're resolving a new type. And before everything, we're gonna check if this is already true. If expression type return type expression dot expression. So it's looking up in something which is not the structure, and that's correct. I think this is the edge case, so I'm using this wrong. So this is the generator. Let's see if so now I'm actually typing more here. So we have a declaration token, and we're assigning the size. This is looking very ugly. I'm gonna clean this up a little bit, but it's correct. So I'm just gonna do it off stream. And now the token A, we have to see what the token A is. And this is interesting. So the token A is unsigned 8 bytes. This is really cool. So even though the A, no, so we have to follow this down here. So the identifier token is this entire thing. And the dot A is going to be 8 bytes, because that's 8 bytes there. If I'm saying like token new, that's going to say that the token token value, no, token dot A, I'm still getting A. Typer failed. This is a typer failed. Oh, maybe I'm doing something wrong. Yeah, here we go. I don't know what was happening there, but basically the dot array, the dot new, is an array of 3 unsigned 8 bytes. So we know the type of this element, which is very cool. The theme might be a little bit wrong. Yeah, the theme might be a little bit wrong. So we're not doing any type checking. We're just generating the type and doing type inference. Yeah, so actually let's generate some code for this. Wait a second. So the token new is an array, so let's do token new of 2. That should generate a U64. Yeah, so the argument here is a U 8 bytes, because it's having a deref and it's doing all this crap. I have to fix this. This is like one single type. I probably will write some kind of comprimated, no, what do you call it? Compressed format of this, because I want to have the size, but probably you don't need to know this entire thing. You probably only need to know the struct size and the alignment. Yeah. So this can actually print this entire thing at the very bottom because it's nice to know. But when I'm printing this as like an expression, because each expression has a type, when I'm printing this as an expression, I'm gonna just print one line. That might be easier to understand. And then we have an issue in the generator, because now we're gonna be able to generate those dot expressions. So generate expression. So I'm gonna try to generate code for this. Generate dot expression. Okay, so this is being called. So what do we have to do then? This is the dot expression, so we're gonna try to load, we're gonna have to try to find the address of this one. We're gonna generate the address of this dot expression. So generate address of this entire expression. And then we're gonna load from Rax. And the type I'm gonna give it the expression type. Why the load from Rax is taking in a type is because we have to know if this is an array. If this is an array, you can't load an entire array into memory. So we're basically loading the address. And we're also gonna need it for if we're gonna support multiple types as well. So now the generate address is also gonna track if this is a dot expression. Thank you for following. Welcome to the stream, guys. So let's check if this is a dot expression. This variable is deref. Is that? Maybe we can just check expression kind equals expression dots. So if this is a dot expression, let's see you have something like new. Let's do token IIIC. Token IIC. So this is gonna have this member here. Let's see if it works first. It's compiling at least. So now it's accessing 4 bytes. This argument is 4 bytes, and that's the C, which has the correct type. So we're asked to get the address of this one. Well, we know we can find the address of the token because this is just an identifier, which are presumably being allocated on the stack. We're gonna check that first. So let me just print where things are being allocated. Struct. Yeah. So when I'm computing, when I'm assigning this a stack frame, declaration name, assigning stack, to and offsets. All right. Yeah, I'm just gonna print the size here. With size something. Dang it. It's an H. Alright, so here we're assigning this stack frame. And we should have the token here. Token with size 32. And the size of this structure is 32. So we're assigning this on the stack frame, which basically means by looking at this identifier, I can get the address. So all I know, I know the offset from this variable here. So I know the offset from this one. So I need to just generate the address of the sub-expression and then add the address of this part. So I'm going to recursively call generate address from expression dot expression. And then I have to add to meet some kind of add instruction. Or can we? I'm gonna do the add first. Maybe we can optimize it later. Add some identifier and to the Rex value. So what should this be? Expression dots. We need to know the offset from the dots relative to this next expression here. Can probably just store it somewhere. Like each dot expression is going to have an offset. Typer. Here we go. Type dot expression. So expression type. Should I really do that? Yeah, I'm gonna access the offsets. So the dot expression offset is gonna be member offsets. So we're saving the offset there. So I only need to add that tiny offsets. Undefined reference to D. Am I getting right into the right thing now? I'm printing token value. Token value is a very big value. Which might be true. I'm going to try to assign this A. So token A is something. Token A is equal to 50. It doesn't crash though. So the token value is 50. That does actually work. If I'm assigning this to U64, I'm using U64 because I don't support loading smaller values. So now I can do like dots IIIC. Oops. We're using the same one here. And there it works. It's still 50. So let's make something simpler. I want to print it like, I want to check if I'm setting the right member. I'm gonna have like C, D, E. So this is a token structure, and I want to set A equal to 1. The way I pronounce generate is a UK accent. Like generate. Generate! I'm saying generate. It's because it's called like generere in Norwegian. Generate. Generate, it's called. Thank you very much. Let's say A, B. A, B, C, D, E. And then I'm going to cast this to a, I don't support casting, which is fine, as long as I'm making sure this is going to work. So it's a U64 pointer, which is a pointer to U64, which is the address of token. And then I'm going to say for I in 0 to, let's do 0 to 0, 1, 2, 3, 4. Thank you for following. And then we do the value at pointer plus 1. Oh. Invalid struct member. That's good to know. And it's working. It's actually working. What the fuck? Let's make this a union instead. Because either one of those is going to be the same. Fuck. Dang it. Union? What the f... Why is the typer failing on this? I don't know why it doesn't work here. Maybe I didn't save it completely. Or is there some random shit happening? Anyway, so we're getting like the first member has a value 5. And that's because I'm assigning it first 1, 2, 3, 4, 5. So I need to test this a little bit more thoroughly, but I think it works as expected per now. So the only thing I want to change now, I want to have like pointer is going to be converted to, like if I'm having a dot and token is a pointer, it is going to fix it for me. So what I want to do, I want to have pointer, we can still like call that pointer. So I'm going to make a new variable, which is a pointer to token, which I don't really need to write. We can just say this is the address of token. Token address. And then I'm going to say token address of A is equal to 1, and so on. So instead of this, I'm doing token address. And then I'm printing the pointer. Oops. Yeah, so now it fails with the typer because we have something which is a pointer to something. That's probably an assertion fail. Yeah, so it is the structure. So that's a problem. So we're basically gonna handle this. The parser doesn't know anything, so the parser is just gonna like construct this tree. So we have to modify it somewhere. What VS Code theme is this? Thank you very much. This is called Everforest Dark. Really looks like. I have been coding for a little bit too long because my brain started to shut down a while ago. So I usually, when I'm off stream, I'm taking breaks between, and it is actually a huge difference when I'm coding off stream. I'm not, yeah, unfortunately. Okay, so we're gonna go into the typer. We're gonna fix it in the typer. So handling this dot expression. So what if this is a pointer to a pointer? Okay, so we have a dot expression type. We know what the expression is. Thank you for following. So we're going to be modifying it here. This is correct though. No, before we look it up in the member, because we're looking up the dot expression type. Thank you for following. We need to change the tree a little bit. Yeah. We need to change the tree a little bit. We need to check if... Thank you for following. If the dot expression type is a type pointer, which means that what this is pointing to, like we have a dot expression which is a, and this is pointing to something which is a pointer. We have to say, as long as that is a pointer, I'm gonna do it like while. As long as that is a pointer, we're gonna make a new node, which is like a deref, because the compiler is gonna understand that you try to do something like dereferencing it first. Thank you for following, Nuka Cat. So I'm gonna make a new unary node. Oh my god, that's so much followers. Thank you very much. I'm gonna make a new unary here, which is a deref. So this is gonna tell what this is supposed to deref. So the operator, I don't think I need to write the operand operator. This is just for error handling. And if I'm having a save fault, I'm gonna fix this operator. The operand is gonna be the dot expression. So now the dot expression is gonna be the operand. And then we're setting the dot expression equal to the expression, like to the unary expression. So we're now saying that what I'm gonna deref, like what I'm gonna access the member of is this dereft. And then I need to update the type as well. So now dot expression type is equal to dot expression type pointer to. It is what it's pointing to. And I don't think I need to do anything more. Fuck. Inferring type kind. We need to update This is what it's pointing to. That's a pointer. Is this happening? Question mark. Inferring token address. This is in the typer stage, typer 256. Lookup member instruct. It is going to type the expression first, which happens to be this. So this is going to be like a primary expression, I think. Yeah, so it's going here. Okay, so it's stopping. It doesn't go in here. Oops. Oh, there's some issue here. Dot expression type. This is supposed to be type kind. Okay. So I'm accessing token address B. We have a segfault here. Pointer 2. Are we switching the expression first? This is wrong. We're first switching the type. Then we'll make a new unit expression. We are having a struct member of something which is a pointer. And then we assign the dot expression with a unary. I think that's the issue. Fuck. It's failing in here. So it goes in here, we have a pointer. Dot expression type. We're setting this expression type equals to what it's pointing to. I can do this, right? Yeah, I can do this. Now I'm saying dot expression. Operand is equal to dot expression. Thank you very much, Bright. Coding and speaking at sometimes very exhausting. Yeah, it is. Sometimes, especially in English. This is compiling into x86 assembly or x64 assembly. Everything here works. But we can assert that the dot expression type is something. So this is nothing. So if we have a pointer, then it should be pointing to something. 194. It is pointing to something here. Oh. It is trying to be difficult. It's annoying me. So dot expression type is equal to type. Or we're fixing it there. Maybe it's supposed to be like this. Floating points. Is it really done? Doesn't seem to get there. Oh, I'm actually done here. So it is working, okay. So let's see token address B. So this is assigning binary equal. This is token. So the token identifier is a structure, which is correct. So we need a token address. Here we go. So token address, it is a pointer to this kind of structure. So inference is working. And when I'm dereferencing this, I'm getting a strict size of 40. And when I'm then doing dot, I'm going to get an unsigned 8 bytes. Floating point exception. So the floating point is when I'm assigning the stack, it is giving me 40. So when I'm allocating this new kind of unary expression, I have to type it, I think. I have to type this new unary expression. Something is not typed here. I'm assigning stack token with size 40. And then let's do this before I'm aligning. Name size, offsets, declaration, type size. All right, so I'm assigning stack token address with size 0. Declaration pointer, declaration token address. So this has size 0, which doesn't really make sense. Yeah, that kind of makes sense. That is making perfectly sense. Because the unary expression I have to make a new pointer. What that is pointing to. When I'm inferring this thing, how am I really inferring it? I think I'm inferring it wrong. When this is getting the address of this, I'm basically making some kind of pointer. I'm making whatever this is. So when I have this starts gonna generate the address of this token. And when I'm generating this, I think I'm allocating a new like pointer type. I should be allocating a, like I have to call a function which is setting the pointer size automatically. I don't think I'm doing so. So this is if I have think. Oh, it's right in front of me. Okay, it's right there. I did not actually know where it was, and it's right in front of me. If I'm typing a fucking unary expression, I'm gonna make a new pointer type. Luckily, I found it. This is gonna be a new pointer instead. So this is gonna help setting the size correctly. And it's working. It is actually working. I'm gonna fix this printing right now because it's annoying me. So then I think I can say that structures are working now. When I'm printing this code unit, I'm printing a scope. I'm gonna print the types here. I wanna print this entire thing. So I'm gonna print true on this type. And for variables, I'm also gonna print like true. And the print type is gonna take in a boolean. I don't find a better name now. I'm gonna print all. That's gonna force to print everything. If that is a structure, it's gonna print print struct with print all. That's the only place I'm gonna use it. So this takes in a boolean value print all. I'm not really caring about this as good code because this is just for debugging. Struct size. Sorry. So I'm gonna say if print all return. So if print all is equal to false, oops. If not print all, I'm gonna just return. And then I have to, whenever I'm calling this print type, I have to call it correctly. Here I'm printing, if it's a pointer to, I'm gonna just give it print all. Oops. There, we have to change something. Print type. Here is false. Is this the struct member print structure? Yeah, print all. Print type and print type. That's far better, I believe. So now this is only like C is equal to token address, which is a pointer to a structure. And the deref will just be the structure. This is much cleaner. That's great. And I'm having some warnings as well. Type unary 296 in typer. 296. I don't know if I need to type the unary here. Let's think a little bit. Am I really resolving anything here? Am I resolving anything new? Do I have to change the typer when I'm doing this? If I'm typing the unary expression, that's going to change it accordingly. So the question is, do I have to do something here? Like, what happens if I don't know something? It's going to say while that is a pointer. This is going to type a dot expression. This is going to happen each single time I'm going through this pass. And if this is already typed, I'm going to just return. And I'm typing the sub expression first. Typing the sub expression. And if dot expression type. Okay, so here I'm setting the type. Here I'm typing stuff. Okay, and here I'm saying type resolved is equal to true. So is there something I don't know what is? Like, this is a unary deref, and we're actually setting resetting the type here. We're setting the unary type. So we can't type it. I don't know what this is gonna do. I have to sit down and take a look at it. Anyway, it's starting to work now. I'm gonna remove this stack frame printing, and then we can make some cool programs. We're gonna test if this actually works. Tree printer. This is in a generator. I'm just gonna comment it out. I probably is gonna need it later. There we go. So now we can, if I'm not mistaken, we can do all kinds of things with pointers, and type defs are working. Actually, inference are working now. It's just gonna take multiple passes. I don't know how slow it is. It's probably gonna be pretty slow. And I don't know, the type inference probably just work on, is it like local or global? I don't know. We're kind of typing this entire thing. Anyway, good night or day, whatever you are, everyone. Good night. Thank you, Dr. Drill, for following. Welcome to the stream. Thank you. Thank you very much. All right, let's delete this stupid stuff there. Actually, I want to do one more thing. I have to Google it. x64. It's gonna be like load. It's gonna be load. What is it called? Like 8-bit, 16-bit. Didn't I have this guide to assembly here? So now we're currently just storing this entire thing, which is wrong. If I have a smaller data size, I only want to store like 8 bits or 16 bits or 32 bits. And additionally, we have like we have RAX, which is the double of this size. So this is moving the bytes. EBX into EAX. Like I want to store just either like 8, 16, 32 or 64 bits from a register to some kind of address. I want to do that. And I want to load it as well. So I want to load the value at address racks into RAX, but I want to load like only like 8 bytes. I don't want to load 8 bytes all the time. I want to be able to say how many bytes I'm going to load into the register. Thank you for following. It dereferences a pointer, yeah, thank you. It's instead of star in C. And I'm using star instead of and symbol in C, like address of. Move. So that's 1 byte, that's suffix B, and word is 2 bytes. That doesn't make any sense, but okay. Double word is L, and chord is Q. That makes sense. So move source to destination, move this source to destination. Sign extended. So I can use that one, and I have to make one of these extensions there. Convert the byte in AL to double word in EBX. Move 0 extend byte L. What does L mean? Oh, that's a double word. So you're actually specifying, am I getting this right? You're specifying, you have to specify 2 letters. You have to specify the source and the destination. Is that correct? It's called luxury. Is there something who knows, someone who knows x86 assembly? Please don't say rest. That's right. Where's my loading? So the load from racks and store to racks address. So I'm gonna store RDI to racks. But I want to know, like I know the type. I'm taking in the type. So I'm gonna check the size of the type, which is supposed to be like a simple basic type. 4, 1, 2, 4, or 8. So in case this is like 1, I'm emitting something, I'm breaking. And case 2, 4, and quad. So if I'm gonna move RDI to RAX, I'm gonna do that. So it's like move source. Thank you for following. Move 2 bytes. I don't know what to search for. Okay, so you're doing move B. It says AL. So do I have to do like this is D DI? Which is the what is the registers? DI. I can't really access the smaller part. Maybe I can just try to, this is moving a byte. This is much simpler in ARM. Much simpler. Copy the 1 byte AL. Sign extended to 4 byte EDX. RDIte 2 bytes. Version. Okay, there we go. EAX EDI. So we can do that. This is DH. This is confusing as hell. Move byte, move word. Okay. So I don't need to change this to anything else. Move byte, move word, move long, move quad. Is that correct? And for storing, so I'm moving RAX. So this is also using the same thing. Move B, word, L, Q. Okay. That's weird. It's a weird language or a weird instruction set. So let's test if this is working. So I'm going to iterate from I'm gonna have a like, because this is only getting I can have a something which is just iterating. So for I in 0 to 500. And then I have a counter which is a char which is equal to 0. And then I just print counter C is equal to C plus 1. C is a char. Oh, it's already existing here. That's fine. I can use a different letter. All right, inference failed. There is something weird. Declaration type failed. What is failing? Variable is not declared. RD and I not allow we move bytes. This is 69. Output's number 69. I can't use this with move bytes. Error output is clean and very easy to read. Thank you very much. Okay. Oh, this is so confusing. Move bytes to the BL. DL. Because Rax is not allowed with move bytes. Move byte into RL. It's loaded. It's happening that many times. Doesn't seem to change the value though. Am I storing this? So this is a 1 byte, and I'm moving DL. I don't know. I'm gonna just use move. I'm just gonna use move, and then we figure it out later. Just use move. We can still use just U64. So now it's incremented. It's incrementing fast though. Yeah. So let's make this a U64. Then it's incremented to 500. Okay. Let's make a game. Can can I read stuff from memory? Some from input. If I read some input arguments from the user, how to read input C. How I get printf, I'm calling from stdlib. So GCC is providing it. So we're going to be using getchar. This is returning something. That's returning a char. I kind of have to get numbers to work first, like letters. How to load and store x86. Wait a second, we can do Compiler Explorer. That was a good idea. We can just see what they're doing. Yeah, I've tested some stuff here. So I'm gonna print the char C. This is moving a byte in there. And then this call. This is moving 0 byte L. If I have a different char, where is that happening? Okay. So it's moving into EAX. So this is what I'm after. So this is going to move bytes from AL to something there. Okay. Where is that again? So move CLB to EX. Okay. And move byte AL store to racks. Move byte AL. This is DL. I'm moving DL to something. And so I think this has to be correct as well. 0 byte Q. And I can just say EAX or RAX. So you can give me counter 0, All right. So get counter equal to 0. I think I'm moving 0 somewhere. I think some of these instructions are wrong. What am I trying to do? I'm trying to load some kind of 8-bit number to a 64-bit number. Long j is equal to 0. And then I'm going to say c is equal to j. So this is first loading j, which is a long. So just move q. And then it moves a byte from AL. So when moving from a register, I need to use AL. So DL, is that correct? I'm doing the opposite direction. J is equal to C. Zero BQ. SBQ, not CBQ. I don't know what S means. Emit. I don't know. I have to just experiment with the compiler explorer. Because this is a signed. If it's an unsigned long, it's doing the same thing. Here we go. So moving R into RAX, and it's loading. This is loading the address of that variable, and it does move SBQ. So from this is supposed to load one single byte. No, I'm not using LLVM. I'm generating the assembly directly. Yeah. Move SBQ. Where am I assigning that one? Assigning it to 0 there. It doesn't really matter where I'm assigning it. That's weird. Anyway, I'm assigning it. I'm moving 1 into something. This is gonna get the counter value. Then I'm adding those two. And I'm pushing racks. Then I'm computing the next adder, which is the same. Popping RDI. And then I'm moving DL, which I think is wrong, to RAX. So I think this instruction here is incompatible with this one for some reason. How does it run assembly straight from the file? Yeah, I'm compiling with GCC, or GCC assembles it for me. Move SBQ. gonna try both directions. J is equal to J. Oops. So move SBQ and just move a quad to memory. As long as it's zeroed, I just want to zero it. Move byte AL. That's a quad word though. RDI. Oh my god, this DI. Not DL. What is DL? DL is apparently nothing. It says DIL. Byte 0 to 3, that's EDI. DI, RDI. This is DIL. And there we have something working. So this is now apparently a signed number. So it goes up to 127 and then wraps around. Okay. So that's DIL. We're gonna deal with casting later. So DIL, then you have DI. So this is gonna be DI. Oops. And EDI and RDI. And SBQ, I'm probably thinking like SVQ, LQ, and move Q. Something like this, I don't know. Oops, I didn't mean to do that. Thank you for following. Welcome to the stream. It seems that chars are working correctly. I want to test that it works with U16 as well. So I'm gonna go up to like 70,000. U16. That work? It's going not as far as I would have thought. Like 5 or something. How far did it go? Okay, 32. That's a signed 16-bit number. So it seems all are signed. But that's really what we need at this current point. So let's try to read something from the input. Didn't I have that? No. So I'm gonna go get char. Get a char. And this is returning an int. Enter a value. print char. Is get char gonna block? Reads a line from std in get string. So now that's char buffer there. Okay. And it returns a char. So let's try to print something like that. I'm gonna call getS. And I'm gonna make a buffer first. Yeah, so kind of buffer. It is an array of 100 chars. And I'm gonna use this with the buffer. And then I should have like a while loop. I'm gonna just say for I in 0 to 99, just to be like safe. And then printf char, which is buffer of I. I'm just gonna see if that works. I'm making data not declared. Yeah, I can't use those. Thank you for following. Typer failed. Doesn't know the type. It doesn't know the type. Why does the typer fail? Get function is dangerous and should not be used. What the hell? Hello. So we're getting that. The get function is dangerous. I don't care. I don't really care about that. Yeah, we should have a while. The thing is that I don't have some like continue or break. I want to have continue or break statements. And while loops. We can make while loops real quick. Let's start by making while loops and break and continue. Let's just use while loops. I'm going to start by just using while loops. Thank you for following. So the Elixir is going to have a new keyword. It's going to have after while. It's going to have, I'm having the keyword while. Then I'm just going to go into the parser and fix it. That's parse if and parse while statement. So it seems like the Elixir is already at the if. So this is going to start parsing the condition. Conditional condition is equal to new statement. Conditional. And then we say the condition is equal to parse expression. And is that an if? That's not a conditional, that's a loop. Loop condition, loop body is equal to parse compound statements. I think that will parse it correctly. I don't think we need anything else. Return statement loop. Parse the while statements. Thank you for following. So for if, we're gonna add while. So that should be parsing it. I don't know if the printer is capable of printing that. Parser. What the f... Did you mean parser? I'm saying that. There is something weird with the compilation there. That's why I have this stupid things. Loop end. First of all, let's write a loop statement. So I'm gonna have like iterator is a u32 equal to 0. And while iterator is less than 40, I'm just gonna loop, and we're gonna be printing this number. And we have some kind of loop segmentation fault. So I'm looking for the init, and that's not really present in all the expressions. Print function, print structures, structure. Print scope, print statement, print loop. So we don't have an init. It's gonna be like if we have an init. Because we're using the same loop for the same construct for many different loops. Condition, we're always going to have a condition. Like what parses, like the expression parser, that's going to fail. Yeah, so we have to have some kind of condition. This is optional. Inferring I, so it's happening in inference as well. If loop, init statement, and we're going to track this as well. If loop, pass statements. Is it typing this? It's typing. I guess we have a segmentation fault after. After that, let's see how the code looks like. We have a loop condition. Thank you for following. Identifier iterator is less than a number 40. And then the body is just call printf with a string d, identifier iterator. Thank you for following. Expression binary equal iterator plus 1. So this probably needs to be the same size before we implement casting. Oops. Why the hell would you have a segmentation fault there? Well, iterator. Oh, it's generating the code here. So this will be like if pass statement I misspelled it. There we go. Oh, this is while iterator is less than 40. Iterator plus 1. So the condition is here. If the condition is wrong, so we're comparing this condition to 0. And we jump to loop end. And we're generating the body. I don't understand why that shouldn't work. Iterator less than 40. Hello, Koroxer. Yeah, for loops, but not while. Yeah. Unfortunately, we're gonna implement them though. We're trying to implement them. Node pointer. I haven't been there. And break keyword, yeah, that's that's really nice. Do you use VSL? Yeah, I don't know if this is VSL2 or VSL1. It's one of them. That's the while. So we're in this loop. It's moving 40. First is moving like 0 to move quad. So if this move quad is wrong, everything is gonna fail. And you're comparing those. Just 0 extending. I don't know why I'm comparing 2 times. Yeah, I'm comparing with 0 here. And jump if not equal. Loop end 1. Which is here. Otherwise I'm just jumping back to start. And now I'll loop 2. Like well 40. Oh fuck, I'm using this before. I didn't see that. I'm sorry, I didn't see this. That's supposed to go after. Okay, so this sequence of numbers, is that probably the printing? We're getting like 1 to 39. Yeah, because if it's 40, it's gonna break. So now while loop works, and I'm gonna get the buffer. And since we don't have break, like break we have to track if we're inside a for loop. So how do we know if we're inside a for loop? Or inside some kind of loop? You can take a look at the Can't think now. Let's just have a counter. Is equal to 0, while counter is less than 100, which is the size. I'm gonna not care about the overflow. So while the buffer of I is something non-zero, we're gonna print that element. Counter is defined 2 times probably. Oh, it's not defined. I. Buffer of I, let's have a, let's use counter instead. Typer failed. So then I'm echoing it. It seems to work. I don't know. Yeah, I'm gonna just make one simple thing for testing if I can print a file. So let's say this program is gonna compile something. We need to call like, am I including? Can I call f open, and the first argument is the file, which is a string. So I'm gonna first check if argument count is not equal to 2. I'm gonna return an error. So we have 2 arguments, so I'm gonna get the second argument, which is argument 1, and we don't have strings. Fuck, I'm just gonna stop there. I'm very tired. Let's do one more thing. Let's have this board. Let's let's have a structure. So it's going to be called number, which is a structure. Number is a U64. And then I have a print number, which is a function, which takes in a pointer. This is a pointer to number. And it's going to print what this is pointing to. And I should be able to do number is pointer dot number. So number has the type number, and number dot number is equal to 45, and then we're going to print number. So I'm going to give it the address of number. So number is 45. So I'm accessing the number even though I'm passing the pointer here. So we don't need to use arrow. That's very cool. And I'm going to press the numbers here. Let's make a pointer, which is going to have the address of number. And let's place this up here. So address of number, and number is defined down there. So that we can check if the time prince is doing this correctly. Pointer. It is still working. So that's really cool. I'm actually happy. after all, I'm very happy. There are still like a lot of issues, and I'm gonna clean up the code. So I'm probably not gonna be streaming tomorrow. I need to clean up the code a little bit. But yes, things are starting to work. And I'm very happy we got the type inference to work. So even, let's see, let's do one more thing. Like, I don't even need to print it. I'm just gonna write it. So we have a data, which is equal to test. Test is equal to OK. OK is equal to P, and P is equal to something like this. So we're defining that down there. Actually, P is going to be temp, and temp is defined down here to have the type pointer to char. So you can still use temp here and define it down there. I'm just going to see if it yields the right tree. So does it type this entire thing? We're expecting a pointer to char on each of these. So data test, everything is a pointer to. That's so cool. I'm so happy with how this works. But I guess there's a better way of doing type inference. I'm probably gonna have like a hard time if I'm implementing templates. I'm not sure if I'm gonna implement it though. It's gonna be really similar to C. Anyway, I think I'm gonna be going to bed now. But hello, this is really cool. This is awesome. So I'm committing now. Let's commit first. What they would do, like added. What do we do? Like added structures and improved type inference. Yeah, cool. Then I'm gonna go to bed. Mellow trash. All right, so let's take a raid. Twitch. I'm probably gonna start doing shorter streams because I'm kind of, yeah, I don't know. I'm getting very tired by taking so long streams. Make longer. Okay, we're gonna raid Piggy Bank Studios. He has really like quality streams. He's streaming, I think he's streaming game development. So we're gonna go and raid Tyler. I think that's his name. 9 hours is long as fuck. Yeah, kind of. Anyway, good night, and I hope I see you later. I'm gonna be trying to stream in like a few days. I'm just gonna clean up the code first. Anyway, have a good night, and thank you for watching.
How long it takes to compile and run on the second version?